Time doesn't just pass, it can be bent, throttled, and in the right gravity, almost switched off. Out there in the universe, clocks don't agree. Seconds stretch into eternity, and the future can arrive at different speeds. So where exactly does physics let time slow to a standstill? And what would it cost to go there? Imagine a universe where now is not a moment, but a negotiable contract, signed by speed, gravity, and information. If that contract can be rewritten, then time is not merely measured, it is engineered. We live as if time were the one constant we never had to earn, an invisible allowance that arrives uninterrupted for everyone. But physics treats that comfort like a local habit, not a universal guarantee, and it invites a more severe question. What would it mean for time to reach zero, not as metaphor, but as a physical limit? To ask that seriously, we have to separate three things we usually fuse into one word: clocks, change, and causality. A stopped clock is trivial, a halted sequence of events is something else entirely, and a world where cause and effect can no longer advance is a boundary where our familiar logic begins to fail. This film follows the places where that boundary is approached, first in the clean mathematics of motion, then in gravity's ability to reshape what simultaneous even means. We will see how the universe keeps its promises with ruthless bookkeeping, and how every apparent shortcut is paid for in energy, distance, or perspective. Then we return to Earth, because extraordinary claims must survive ordinary laboratories, where atoms become pendulums and nanoseconds become terrain. There, time is not an abstraction, it is a quantity you can compare, trade, and watch. Drift apart under conditions so small they feel like cheating. Next comes the quantum domain, where time passing can be rephrased as a state changing, and change itself can be inhibited by relentless attention. The idea sounds like folklore, until experiments force us to confront a deeper rule. Observation is not a passive glance, it is a physical interaction with a cost. And when we ask why the everyday world does not freeze under its own constant monitoring, the story turns colder. The arrow of time enters, not as a poetic direction, but as a statistical pressure that makes memory possible and erasure expensive. Here we begin to see that stopping time is not only about slowing clocks, it is about confronting the machinery that makes one moment different from the next. Finally, we reach the frontier where our best theories stop agreeing, and time becomes the central contradiction they cannot share. Some equations will insist that the universe can be described without a flowing time at all, while our experience insists on a relentless before and after. Between those two claims lies the most unsettling possibility: that the flow we feel is a story written on top of something more silent. So this is not a quest for immortality, or a trick for outrunning the calendar. It is an audit of reality's ledger, asking where time can be slowed, where it can be held in place, and what physics demands in exchange for even approaching that limit. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey across relativity, metrology, quantum measurement, thermodynamics, and quantum gravity. We track time to its sharpest edges, where familiar intuition breaks cleanly. By the end, the question is no longer how to stop time, but whether time was ever fundamental to begin with. What if time is not a river, but a setting the universe can change under specific physical conditions? What if physics can slow it, tilt it, or drive it towards zero without breaking any clockwork? Our question is not poetic, even if it sounds like myth. It is operational, framed the way an engineer frames a limit. What would it mean to stop time, and where does nature permit anything close? For centuries, the default answer was Newton's, and it felt almost unavoidable. Time was absolute, the same everywhere, flowing evenly, indifferent to motion and matter. Space was a stage, rigid and silent, where events happened like actors crossing a fixed floor. Clocks were assumed to agree if built well and compared carefully, because time itself was assumed to be universal. That picture works for cannonballs, planets, and daily life, because everyday speeds are tiny compared to light. It also works because our senses evolved in a regime where relativistic effects hide beneath measurement noise, yet it fails when we demand a deeper rule that all observers can share, regardless of their motion. The first crack appears when we ask a simple question with sharp consequences. If you move fast enough, do you still share the same now as everyone else? In the late 19th century, physicists tried to understand light as a wave in a medium, an invisible ether filling space. Experiments, most famously Michelson and Morley, kept returning a stubborn null result, as if Earth's motion through that medium could not be detected. Something was wrong with the background assumptions, not with the instruments. Into that tension stepped Einstein, who treated the puzzle as a principle rather than a patch. Einstein's special relativity begins with a stubborn fact about light. In vacuum, light travels at a speed we call c, about 300,000 kilometers per second. More shocking is what experiments imply, and what Maxwell's equations already suggested. Every inertial observer measures that same c, even if they are moving. That statement is not a detail, and it is not a preference. It is a constraint that rewrites time and space, because it forbids the old arithmetic of velocities. If c is invariant, then distances and durations cannot remain universal. They must adjust so that all observers still compute the same speed for light. Visually, imagine a beam of light fired down a long corridor in a moving train. A passenger sees it travel straight down the car, a clean back and forth bounce between mirrors. An observer on the platform sees a diagonal path, longer than the passenger's path, because the train moves during the flight. Both observers still measure the same c, so the only way to reconcile their measurements is for time itself to stretch. This is the first framework where time becomes something you can manipulate physically. Not by willpower, not by broken clocks, but by changing motion in a precisely defined way. The universe does not ask what you believe about time. It asks how fast you are moving relative to someone else, and it enforces the consequences. To see the stakes, imagine two identical clocks, synchronized side by side with care. One stays on Earth, ticking on a laboratory bench under steady fluorescent light. One rides a spacecraft that accelerates, coasts, turns and returns, its display glowing in a dark cabin. In Newton's world, they reunite and agree because time is a single river. In Einstein's world, the travelling clock can come back behind. The mechanism is geometry, not mechanical failure. Space-time replaces separate space and time with a single structure, where events have coordinates and intervals have invariant meaning. Motion through space changes how you slice space-time into space and time for your own bookkeeping. The clock does not malfunction, and its atoms do not hesitate. It follows a different path through space-time, and the length of that path is the time it accumulates. This is why the so-called twin paradox is not really a paradox. The travelling twin changes frames when accelerating and turning around, which changes how they connect distant events into a consistent timeline. The stay-at-home twin remains in one inertial frame for most of the story, and their space-time path is different. In space-time, different paths between the same endpoints can have different lengths, and time is that length. Special relativity also sets an ultimate speed limit, and it is deeper than a warning sign. It is not a limit like a speedometer red line, where you could still push harder and break something. It is a limit on cause and effect, built into the structure of space-time itself. If information could travel faster than c, different observers could disagree about what caused what. That disagreement is not a philosophical nuisance, because it would allow causal loops. A message could be sent into someone's past in some frames, making effect before cause more than a word game. Physics protects itself from that contradiction by placing c at the boundary of influence. The speed of light is not merely fast, it is the edge of what can be connected by a signal. So c becomes the boundary of communication. The fastest any signal can carry influence. It is also the fastest any object with rest mass can be pushed, no matter how powerful the engine. The closer you get to c, the more the universe resists, not by friction, but by geometry. The rules of addition for velocities change, and the remaining gap refuses to shrink normally. The key quantitative tool is the Lorentz factor, gamma. Gamma equals 1 divided by the square root of 1 minus v squared over c squared. It looks simple on the page, like a neat algebraic ornament. It behaves like a trap, because it stays near 1 for small v and then rises violently near c. Time dilation follows immediately, and it is not optional. A moving clock ticks slower by a factor of gamma compared with a clock at rest in your frame. The moving clock's proper time is smaller than your coordinate time, even though its mechanism is perfectly healthy. Each observer still sees their own clock tick normally, because proper time is always local. This is where intuition breaks, and it breaks cleanly. There is no universal present that everyone shares, no single master time that all clocks obey. There are only local clocks, and the space-time intervals between events, which remain invariant even when time and distance reshuffle. Now becomes a slice you choose, not a slice the universe hands you. Now we build the first recipe for stopping time, at least in a controlled approximation. Take a traveller and increase their speed relative to Earth, and keep them moving fast for a long while, as V rises, gamma rises, and the traveller's seconds stretch compared with Earth's seconds. The traveller's heartbeat, chemistry, and thoughts remain normal in their own frame, because their proper time is their reality. At modest speeds, the effect is tiny, and it hides inside rounding errors. At airline speeds, it is measurable with atomic clocks but invisible to biology, a few nanoseconds gained or lost. At orbital speeds, it becomes a real accounting term, one that engineers must include. At near light speed, it becomes the central story, because the difference is no longer subtle. Push V closer to C, and gamma grows without bound, climbing a curve that becomes nearly vertical. The graph is an asymptote, a line you approach forever without touching. You can get arbitrarily close to C, but the last gap never closes. From Earth's perspective, the traveller's clock can be made to tick arbitrarily slowly, as if it is trying to freeze. In that limit, time nearly stops for the traveller relative to Earth, even though nothing stops locally. The year on Earth could correspond to days, minutes, or less on the ship, depending on how close to sea you cruise. The traveller does not feel frozen, and their cabin does not become a still photograph. They feel normal, while the outside universe races ahead. This is not science fiction, and it is not a trick of perception. It is a direct mathematical consequence of the invariant speed of light, tested in laboratories and in the sky. If C is fixed for everyone, then time must become elastic, because something has to give. The Lorentz factor is the price of keeping light honest, yet the recipe hides a brutal barrier, and the barrier is not technological optimism. If time dilation grows without bound, what stops us from reaching the point where it is infinite? Why not accelerate a massive object all the way to C and truly stop its time? The answer is energy, and it arrives with a hard edge. In special relativity, momentum and energy grow with gamma, and they do not grow gently. The relativistic energy is E equals gamma mc squared, which means gamma multiplies the rest energy itself. As V approaches C, gamma approaches infinity, and so does the required energy. That means the energy requirement diverges, not just becomes large. To accelerate any object with rest mass to exactly C would require infinite energy. No finite fuel, no finite engine, no finite universe can pay that cost. The limit is not a matter of better metallurgy or bigger rockets. This is why C is not just a practical limit. Like the fastest plane or the strongest material, it is a structural limit, written into the way space-time measures intervals. Massive objects can approach it, but they cannot reach it. The closer you get, the more your engine buys less speed and more time dilation, as if velocity turns into a different currency. So the first path towards stopping time is real, but it is asymptotic. You can slow your own aging relative to others by moving fast for long enough. You cannot make your proper time fully halt by motion alone if you have mass. The universe allows you to bargain with time, but it refuses to sell you infinity. Evidence anchors this in the world we can test, and it appears in the rain of particles above our heads. High in the atmosphere, cosmic rays strike atoms and create showers of secondary particles, including muons. Muons are unstable, heavier cousins of electrons, and they decay into other particles. At rest, they live about 2.2 microseconds before decaying. At that lifetime, even travelling near sea, a muon should not reach sea level from the upper atmosphere. The distance is simply too large for a few microseconds, even at enormous speed. Yet detectors at the ground see many muons, arriving like invisible needles through the air. The explanation is time dilation, because in Earth's frame, the muon's internal clock runs slow. From the muon's perspective, the story is consistent and just as strange. Its lifetime is normal, because proper time along its world line does not change. The distance to the ground is length contracted because Earth's atmosphere is moving toward it at near C in that frame. Either way, space-time geometry preserves the same observed facts, and Newton's absolute time cannot. We also see relativity in human timekeeping, where the numbers are small but unforgiving. Astronauts in low Earth orbit move at several kilometers per second, circling the planet in a thin band of darkness and sunrise. Special relativity predicts their onboard clocks tick slightly slower than clocks on Earth, by microseconds over months. Those microseconds are not dramatic, but they are real, and they accumulate. In practice, the full accounting includes gravity as well, which we will reach later. Even before gravity enters, motion alone produces a measurable aging difference between orbit and ground. Time is not philosophical in this regime. It is an engineering parameter, the kind that can break a navigation system if ignored. GPS makes this lesson concrete, even if you never think about it. Satellites carry atomic clocks, and their timing must be corrected for relativistic effects to keep positions accurate. Without those corrections, errors would grow quickly, turning precision into drift. The world we built quietly depends on Einstein's time because Newton's time is not precise enough. So special relativity gives us a controlled dial. Increase relative speed, and you slow your proper time compared with a chosen frame, and the dial can be turned smoothly. The dial has no upper bound in principle, because gamma can grow without limit. The dial is also impossible to turn to infinity with mass, because energy demands explode. At this point, the story meets its strangest traveller, the one thing that always moves at sea. Light moves at sea in every inertial frame, and it never slows. It never rests, and it cannot be caught by any massive observer. If our recipe says time dilation becomes infinite at sea, what does that imply for light? Here we must be careful, because language can mislead us. Special relativity does not allow a valid rest frame for a photon. You cannot ride alongside light and define the usual coordinates, because the transformation you would need breaks down. The Lorentz transformation becomes singular at v equals c, and the normal meaning of at rest disappears. So we cannot say, in a standard sense, what a photon experiences as it travels. The theory forbids the question in the usual language of clocks and rest frames, because there is no photon clock you can carry in a photon's frame, yet the geometry still hints at something extreme, and it does so with mathematical clarity. Along a light-like path, the space-time interval is 0. The proper time between emission and absorption on a null world line is 0, even if the coordinate time is years in some frame. That is a statement about intervals, not a claim about awareness or perception. It is the cleanest limit case of relativistic time. Still, the implication is haunting when you translate it back into imagery. For any object that could follow a null path, creation and absorption would be separated by no experienced time. A photon can leave the surface of a star and be absorbed by a sensor far away, and the proper time along that path is 0. The universe can connect distant events without proper time elapsing along that trajectory. Light, then, is the closest thing we have to a timeless traveller. It crosses interstellar space while, in the language of proper time, no time passes along its path. It is not a loophole for us, because we cannot become light without losing rest mass. It is a boundary condition, a sharp edge where our usual intuitions fail. This boundary sharpens the central question, and it points forward. If motion can slow time dramatically but never fully stop it for massive travellers, where else can the universe push clocks towards stillness? If c is the limit in flat spacetime, what happens when spacetime itself is curved? What happens when the stage is no longer rigid and the geometry can deepen into wells? Special relativity gives us the first crack in everyday intuition and the first recipe for slowing time. It also gives us the first refusal, written as an infinite energy wall. To go further, we need a new ingredient, one that changes not just motion through spacetime, but spacetime itself. Motion changes your rate of time. Gravity changes what time even means across space. The next step takes us from fast ships to deep wells, where the darkest clocks in the universe keep time by almost not keeping it at all. Motion was our first lever on time, but it came with an infinite energy wall. Gravity offers a different lever, because it reshapes the arena where clocks and light must move. Instead of paying for time dilation with ever more kinetic energy, nature lets mass and energy rewrite the background rules. The lever is not a rocket engine, but the geometry that every engine, atom and heartbeat must inhabit. Einstein's general relativity begins with a reframing that sounds like a metaphor, then behaves like engineering. Gravity is not a force pulling through space, as if masses were hooked by invisible cords. Gravity is space-time geometry responding to mass and energy, and the response is precise enough to be written as field equations. In those equations, the distribution of energy, momentum, and pressure shapes curvature, and curvature dictates how objects and light propagate. The equations are compact on paper, yet they encode a whole logic of cause and constraint. Matter does not merely sit in space, it participates in defining space. The shift is subtle, because it keeps the familiar outcomes while changing the cause. When you drop a stone, it still falls, and the arc still looks like acceleration. Yet the deeper claim is that the stone is not being pulled in the old sense. It is following the straightest available path in a curved arena. The force you feel when standing on Earth is often the opposite. The ground pushes you off the natural freefall path. In that view, weight is not gravity acting on you, but your resistance to the geodesic you would otherwise follow. Matter tells space-time how to curve, and curved space-time tells matter how to move. That slogan is compact, but it hides a full geometry lesson. The motion is not arbitrary, because freefall follows geodesics, the straightest possible paths in a warped four-dimensional landscape. A geodesic is straight the way a great circle route is straight on a globe, even though it bends on a flat map. If you could see the full four-dimensional track, the path would look like the simplest possible line allowed by the metric. Visually, imagine a grid drawn across empty space, like graph paper extending to the horizon. Place a massive body into that scene, and the grid no longer lies flat. The lines pinch, bow, and tilt, and the tilt is not only spatial. The time direction, what counts as forward for a clock, leans differently at different depths in the gravitational field. In a more cinematic shot, the grid becomes a translucent fabric of coordinates, and the time axis itself seems to thicken near the mass. This is not just a new picture of falling apples, it is a new definition of what it means for a clock to tick, because time becomes tied to the shape of space-time itself. In Newton's world, time is a universal backdrop, the same everywhere and for everyone. In Einstein's world, time is part of the physical stage, and the stage can stretch, shear, and curve. The seconds we count are not handed down from outside the universe. They're carved out by the geometry the universe contains. Historically, that leap did not arrive fully formed. Einstein spent years wrestling with how to generalize special relativity, which had already fused space and time into space-time. He was guided by the equivalence principle, the observation that free fall erases gravity locally. If a falling elevator feels weightless, then gravity must be something you can transform away in a small region, which is exactly what geometry allows. It is a principle that sounds almost philosophical, yet it becomes a design constraint for the mathematics. The historical backdrop matters, because Einstein was not working in a vacuum. Newton's gravity had explained planets with astonishing accuracy, and any new theory had to reproduce that success. Astronomers had also noticed small anomalies, like Mercury's orbit, that hinted at missing structure. When general relativity arrived, it did not merely reinterpret gravity, it predicted subtle corrections that could be checked. That blend of conceptual audacity and measurable consequence is why the theory endured. In special relativity, different observers disagree about time because they move differently. Their relative velocity changes how they slice spacetime into now surfaces. In general relativity, they can disagree even when they hover, because gravity changes the rate at which time accumulates. Two observers can be at rest relative to each other, yet still age at different rates because they sit at different gravitational potentials. The disagreement is not an argument about perception, it is a bookkeeping difference built into the metric. The key operational idea is proper time, the time measured by a clock along its own world line. Proper time is what your wristwatch records, what your cells experience, and what an atomic transition counts. In curved space-time, different world lines between the same events can accumulate different proper times. That difference is not a trick of perspective, it is a measurable gap that remains after all calibrations. Proper time is, in a sense, the universe's receipt for how much time a particular path actually contains. To make it concrete, picture two identical atomic clocks that meet, synchronize, and then separate. One stays on a mountain plateau, and the other remains at sea level. When they reunite, they do not agree, and the disagreement is not because one clock malfunctioned. The geometry assigned different amounts of proper time to their different paths through space-time. Even the air pressure, temperature, and vibration can be controlled. What remains is a gravitational signature. Gravitational time dilation is the headline consequence. Deeper in a gravitational well, clocks run slower relative to clocks far away, even if both are perfectly built and perfectly stable. The effect is not about gears dragging or atoms tiring. It is about how the metric, the ruler and clock structure of space-time, weights time intervals at different locations. In the language of relativity, the time component of the metric changes with gravitational potential, and clocks must obey that accounting. The phrase "run slower" is not a mechanical complaint. It means that the space-time interval assigns less proper time to the lower clock between two shared comparisons. In many situations, the relationship can be approximated by a simple factor tied to gravitational potential. Near Earth, the fractional difference is tiny, but the logic is the same as near a black hole, where the factor becomes extreme. The same rule that nudges a laboratory clock by a whisper can, in principle, drown a signal near an event horizon. You can treat this as a prediction about signals, because signals are how distant observers compare clocks. If two observers exchange light pulses, the pulse rate received depends on gravitational potential, because the geometry stretches time differently at different depths. The pulse train becomes a kind of space-time stethoscope, letting one clock listen to another through the curvature between them. In practice, the comparison is done with phase, frequency, and timing markers, physics made audible as a beat. In a visual sequence, we can watch a lighthouse on a cliff flash steadily, 1 pulse per second by its own clock. Down on the shore, the flashes arrive slightly slowed, as if the lighthouse keeper had grown lazy. Yet the keeper has not changed pace at all. The shoreline observer is reading the imprint of gravity on the path between them. The air is clear, the ocean is calm, and still the timing drifts, because the drift is not weather, it is geometry. Near Earth, the effect is small but measurable, and that matters because it anchors the story in metrology. Atomic clocks at higher altitude tick faster than clocks at sea level, by a rate that modern instruments can resolve. The difference is on the order of parts in 10^16 for a meter-scale height change, a number that sounds abstract until you remember that atomic clocks can now see it. In the lab, that sensitivity turns gravity into a measurable gradient, almost like a new kind of topographic map. This is why gravity enters everyday technology. GPS satellites sit higher in Earth's gravitational field, so their clocks tick faster than clocks on the ground, and the system must correct for that drift. Without those relativistic corrections, position errors would accumulate rapidly, turning navigation into guesswork. The satellites also move quickly, so special relativistic time dilation slows them, and the two effects compete. The final correction is not optional. It is baked into the system's definition of a second. That combination is a quiet triumph of physics. It means the theory is not merely philosophical, and it is not trapped in distant astrophysics. The same equations that govern black holes also govern the timing signals that guide airplanes, synchronize financial networks, and timestamp scientific experiments. Gravity is not just a pull, it is a timing infrastructure. Every time a receiver solves for position, it is also solving a small problem in relativistic bookkeeping. So the central question sharpens. If motion can slow time but never fully stop it for massive travelers, can gravity push the rate closer to zero without demanding infinite fuel? In special relativity, approaching light speed costs unbounded energy for anything with mass. In general relativity, the cost can be paid by falling into a deeper gravitational well, where the geometry itself changes the comparison. The universe, in effect, offers a different budget, one paid in curvature rather than propellant. General relativity says yes in principle, because gravity can become arbitrarily strong. The universe provides places where space-time curvature becomes extreme, and the strongest of them is the black hole. In those environments, the difference between local time and distant time can grow so large that our everyday intuition collapses. The clock becomes a character in the story, not a neutral narrator. The closer we look, the more time behaves like a relationship rather than a substance. A black hole is not defined by darkness or appetite, it is defined by a boundary in space-time, a region where escape to infinity is no longer possible. The darkness is a consequence, not a definition. What matters is causality. What can influence what, and which futures remain open? In the simplest case, the black hole can be described by only a few parameters, yet those parameters reshape the causal map of an entire region. That boundary is the event horizon. It is not a material surface, but a causal edge, because inside it every future-directed path points deeper inward. The horizon is a one-way membrane for information, drawn not with bricks but with light cones. Cross it, and the set of directions that counters forward in time no longer includes outward escape. The horizon is less like a wall and more like a change in the rules of navigation. The reason is the speed limit from Chapter 1, now applied to curved space-time. To escape from inside the horizon would require travelling faster than light relative to the local geometry, and relativity forbids that. This is not a technological limitation, like insufficient thrust. It is a structural limit, like trying to draw a square circle. Even a perfect engine cannot rewrite the causal structure that defines which paths exist. Outside the horizon, light can still climb outward, though it pays a price. Inside the horizon, even light cannot find an outward route to distant observers. The geometry does not block light with a wall, it redirects what outward means. The outward direction becomes as unreachable as yesterday. In a visual metaphor, the arrows of possible motion tilt until every arrow points inward, as if the compass itself has been redefined. To build tension, we split the narrative into two viewpoints that must agree on facts. One observer stays far away, watching from a safe distance. One traveller falls inward, carrying a clock and sending signals outward. The setup is simple, almost like a laboratory protocol, yet the results will feel like a paradox. The experiment is not about courage, but about comparison, about what it means to read a clock you cannot stand beside. Both observers can be honest, and both can use good instruments. Their disagreement will not be about illusion, hallucination, or bad calibration. Their disagreement will be about how space-time assigns time to different world lines. In relativity, time is not a single universal fluid. It is a bookkeeping of intervals along paths. The universe keeps accounts locally, and distant observers must reconcile those accounts with signals that can be delayed. From far away, the black hole's gravity distorts the traveller's time more and more as the traveller descends. The distant observer compares the traveller's clock to their own, using the arrival times of signals. Each signal is a physical object in the story, a packet of electromagnetic waves that must climb out of the gravitational well. The observer is not watching the traveller directly, they are watching what the traveller can still send. Those signals arrive increasingly delayed. Each pulse takes longer to reach the distant observer than the previous one, even if the traveller emits them at steady intervals locally. The delays are not merely due to distance, like a growing gap in empty space. They include the gravitational stretching of time along the path the light takes. The path itself is threaded through curved space-time, and the curvature changes what 1 second later means along the route. In the simplest black hole models, the traveller never quite reaches the horizon in the distant observer's coordinate time. The approach becomes asymptotic, like a curve that keeps bending toward a boundary without crossing it. Mathematically, the coordinate time required to reach the horizon diverges, even though the traveller's own clock does not. The divergence is a warning sign that the coordinate choice is straining under the geometry. This is where the phrase "time stops" enters the public imagination. The distant observer sees the traveller's motion slow, then crawl, then appear to freeze at the edge. On screen, the traveller becomes a figure suspended against a dark circle, as if the universe paused mid-scene. The temptation is to treat that freeze as a literal halt of life. Yet what the observer is really seeing is the failure of easy simultaneity across a steep gravitational gradient. But the freezing is not a physical jam inside the traveller's body. It is a statement about how the distant observer's time coordinate slices the curved space-time outside the hole. Coordinates are labels, and some labels behave badly near horizons. The physics remains consistent, even when a particular coordinate system becomes misleading. The map can tear at the edges even when the territory remains smooth. The distant observer's evidence is carried by light, and light is also distorted by gravity. As photons climb out of the gravitational well, they lose energy and their wavelength stretches. The process is not like a photon rubbing against friction, but like a wave being measured by clocks that tick at different rates along the route. The same beam is counted by different time standards at different heights, and the count is what changes. That stretching is gravitational redshift. Light emitted near the horizon is received at longer and longer wavelengths, and the received frequency drops towards zero. The traveller can shine a bright lamp, yet the distant observer receives a dim, slow, reddened whisper. The the message is not blocked, it is diluted by geometry. The photon still travels at light speed locally, but its energy budget is reinterpreted by the distant clock. So the frozen image does not remain a crisp photograph at the boundary. It reddens out of visibility, then slides through infrared, then into radio, then toward wavelengths so long the signal becomes effectively undetectable. The scene becomes a fading ember, then a heat haze glow, then a faint radio hum. Eventually the pulses are so stretched that they merge with the background noise. In the visual language of the film, the traveller becomes a smear of colour that thins into darkness. The distant observer sees two linked effects. The pulses arrive more slowly, and each pulse is weaker and redder until the story fades into noise. The traveller appears trapped at the edge, but the evidence of that trapping becomes unmeasurable. The horizon is a limit not only on escape but on communication. It is a boundary where the universe does not forbid messages, yet it makes them costlier and costlier to receive. Time appears to stop, but the evidence disappears. The horizon becomes a limit not only of escape but of observation, because the information is stretched thin across the distant observer's time. The outside universe can keep waiting, yet it waits for signals that arrive ever more faintly. The final moment never arrives as a clean timestamp. The closer the observer gets to certainty, the more the channel dissolves. We can deepen the picture by recalling what frequency shift means physically. Frequency is the number of wave crests per second according to a receiving clock. If the receiving clock is ticking faster relative to the emitter's clock, it counts fewer crests per unit of its own time. The redshift is therefore a direct translation between clocks, written in light. In that sense, every photon carries a tiny affidavit about the rate at which time passed where it was emitted. Now we cut to the traveller's viewpoint, because general relativity insists on local physics. In a small falling laboratory, the traveller is weightless, and local experiments resemble those in empty space. A dropped pen floats beside the traveller, and a laser beam travels straight across the cabin. The laws of physics do not announce the presence of a horizon with a siren. The traveller can still define a local inertial frame, and in that frame the equations look familiar. The traveller's clock ticks normally by its own measure. Heartbeats, chemical reactions and thoughts proceed at their usual pace, because proper time is always local. The traveller can perform the same atomic spectroscopy, the same chemical timing, and the same biological rhythms as anywhere else. The strangeness is not inside the cabin, it is in how the cabin connects to the outside. The traveller can even look outward and see the universe ahead, but that view is not a guarantee of two-way contact. For a sufficiently large black hole, the tidal forces at the horizon can be small. Tides are the gradients of gravity, the difference in pull between your head and your feet. In a stellar mass black hole, those gradients can be lethal near the horizon, stretching and compressing violently. In a supermassive black hole, the horizon can be so large that the gradient across a human body is modest at crossing. Size matters here, because the curvature at the horizon decreases as the mass increases. The traveller does not hit a wall at the boundary in classical general relativity, and there is no local alarm that must ring at crossing. The event horizon is not a physical membrane in the classical picture, it is a global feature of space-time defined by what can reach infinity, not by what a local sensor detects. That definition is unsettling, because it depends on the entire future of the space-time. The horizon is, in a strict sense, a statement about the fate of light rays, not about a local material barrier. Crossing the horizon is then disturbingly ordinary. The traveller can pass the boundary without noticing a sudden change in the immediate environment, even though the causal structure has changed completely. The cabin lights still glow, the clock still ticks, and the traveller can still speak. Yet the set of possible futures has narrowed, and the narrowing is absolute. The traveller has not been crushed at the edge, but the outside universe has been removed from the list of reachable destinations. This is the documentary's central twist in miniature. The outside observer's time seems to freeze the traveller at the edge. The traveller's own time remains continuous, and the edge does not announce itself. The contrast is not a contradiction, it is the price of comparing distant clocks in curved space-time. It forces a question that sounds simple, yet cuts deep. Whose clock gets to define what now means across a horizon? Two perspectives, one reality, held together by geometry. The disagreement is not about who is right. It is about what each observer can meaningfully compare across curved space-time. relativity replaces a single global now with a network of local nows, stitched together by signals that can be delayed and redshifted. The stitching is physical, and it can fray when the geometry becomes extreme. General relativity resolves the tension by separating coordinate time from proper time. The distant observer's coordinates can assign an infinite time to reach the horizon, while the traveller's proper time to cross can be finite. The traveller's world line reaches the horizon after a finite number of heartbeats, even though the distant observer never logs a final pulse. The mismatch is not a failure of logic, but a property of the chosen coordinates. It is a reminder that coordinates are tools, and tools can become awkward in certain regimes. The horizon is a coordinate singularity in some descriptions, not a physical singularity. In Schwarzschild coordinates, the metric components misbehave at the horizon, and the equations look as if something blows up. Yet that blow-up can be removed by switching to coordinates that follow infalling observers. You can choose coordinates that make the crossing look smooth, because the space-time itself is smooth there for large holes. The drama, then, is not a spike in local curvature, but a twist in how distant bookkeeping is performed. A useful visual is a map projection on Earth. Near the poles, some projections stretch distances and angles grotesquely, even though the planet is smooth. The distortion is in the coordinates, not in the surface itself. Near a horizon, certain time labels stretch in a similar way, making reaching the horizon look infinitely delayed from far away. The map can make a finite journey look endless, even when the traveller's footsteps remain steady. So where does the real breakdown live? It lives deeper inside, where curvature grows without bound, and the classical theory stops being a reliable guide. The horizon is dramatic for communication, but it is not where the equations demand infinite curvature. The truly extreme region is where the geometry is predicted to tear itself into infinities. The horizon is a boundary of messages, while the interior contains a boundary of meaning. Inside the horizon, the traveller cannot avoid the centre in the idealised solutions. The future points inward, and every free-fall world line heads toward a region where the equations predict a singularity. The traveller can fire rockets, but rockets only change the path within the future light cone, and the cone itself is tipped inward. The geometry has turned inward into later. Even choosing to accelerate becomes a choice among inward futures, not a choice to leave. The singularity is not just a point on a map. It is a claim that curvature invariants diverge, meaning the geometry becomes infinitely distorted in a way no coordinate choice can remove. These invariants are scalar quantities built from the curvature tensor, and they provide a coordinate-independent diagnosis. When they blow up, it is not a labeling problem. It is the theory announcing its own limit. The mathematics is, in effect, raising a flag that says the continuum description has been pushed past its domain. In that regime, geodesics become incomplete. A freely falling observer reaches the end of their world line in finite proper time, and the classical description cannot extend beyond it. In plain language, the equations stop giving a continuation for what the observer experiences. The story ends not because the traveller chooses to stop, but because the mathematical structure stops being defined. That is a different kind of ending than time stops, and it is more unsettling. This is the core mystery, because our central question depends on what time even means. If the geometry itself becomes ill-defined, then time as a global coordinate loses meaning, and the theory stops answering. We can still compute up to the edge of breakdown, and we can still compare clocks outside. Yet at the centre, the very object that defines intervals is no longer trustworthy. The metric, which tells us how to measure, becomes the thing we can no longer safely assume. The singularity is not a place where time is neatly switched off. It is a place where the concept of time in classical general relativity fails to be well posed, because the mathematical structure breaks. The equations do not say, time equals 0. They say, more ominously, the rules you're using no longer apply. That distinction matters because it separates a dramatic headline from a genuine scientific confession of incompleteness. We can say what the theory predicts on the way down. We can say the traveller crosses the horizon in finite proper time. We can say the distant observer never receives a final crossing signal. We can say that the redshift grows without bound, and the communication channel fades away. These are robust predictions of the geometry outside and at the horizon. They are not metaphors, and they are not optional interpretations. They are consequences of how space-time connects emitter to receiver. We cannot say what happens at the singularity with the same confidence, because quantum physics is missing from the picture. General relativity and quantum theory disagree about what space-time should be at extreme densities. Quantum theory treats fields and particles with uncertainty and discreteness, while general relativity treats space-time as a smooth continuum. When densities become enormous, both frameworks demand to speak, and they speak different languages. The black hole interior becomes a place where our two best dictionaries fail to translate each other. So the black hole becomes both a clock and a warning. It is a natural laboratory where time dilation becomes enormous, and it is also a boundary where our best classical theory admits its own incompleteness. The horizon dramatizes the relativity of distant comparisons, and the singularity exposes the need for deeper principles. The object that seems to freeze time also forces physics to confront its unfinished foundations. It is as if the universe offers an extreme demonstration, then turns the page before the final explanation. The narrative returns to the opening hook, now with sharper teeth. If time is a switch physics can flip, gravity is the finger near the switch, and the horizon is where the switch seems to click for distant eyes. The outside observer can point to an ever-slowing clock and say, "Look, it is almost stopped." Yet the closer the clock gets to that claim, the less the observer can actually read it. The act of observation becomes part of the limitation, not because of human weakness, but because of causal structure. Yet the traveller's experience refuses the simple story. Time does not halt locally at the horizon. The freezing is relational, tied to communication, redshift, and the way distant observers define simultaneity. It raises a quiet question. If you cannot receive the final signal, what does it mean to say the final event happens for you at all? In a universe where information has to travel, happening and being confirmed can drift apart. So what would it mean to stop time according to physics? It would mean driving proper time along a world line towards zero relative to some chosen comparison, without destroying the clock or the observer. It would mean not merely slowing a movie, but changing the space-time interval so that fewer ticks fit between two shared events. The requirement is severe, because proper time is what any physical process uses to unfold. A clock that truly accumulates no proper time would not merely be slow. It would be a world line with no room for change. Black holes suggest an extreme approximation, but they also hide the result behind vanishing signals. The closer you get to the horizon, the more the outside world loses the ability to verify what it thinks it sees. The outside observer can talk about almost stopped, but the almost is paid for with silence. The horizon turns the experiment into a one-way conversation. It is a profound trade. You can approach the limit, but you cannot keep the dialogue intact. That limitation is not a flaw in instruments. It is built into causal structure, because the horizon separates what can influence infinity from what cannot. Even perfect detectors cannot extract information that never arrives with finite energy and finite frequency. The boundary is not a curtain you could pull aside with better technology. It is a rule about which messages have a route. In that sense, the horizon is a statement about the topology of communication, not about the brightness of a lamp. We end this chapter with a bridge back to Earth, because the next step is measurement. If black holes are nature's extreme clocks, we still need ways to test the same principles in weak fields. The drama of horizons is compelling, but the discipline of physics is built on repeatable comparisons. The question becomes how to see the same geometry in places where we can retrieve the data. The laboratory does not need an event horizon to test the logic of proper time. The same equations that predict frozen time near a horizon also predict tiny differences between clocks separated by height. The question becomes how small a height difference we can resolve and how close we can get to a millimeter. At that scale, gravity's time gradient becomes a laboratory signal, not a cosmic spectacle. The mountain and the basement become a miniature version of the black hole story. The grid that warps around a planet is gentle, yet it is still a warp, and our clocks are now sensitive enough to notice. Because if time can be warped by a planet and nearly frozen by a black hole, then the switch is not myth. It is a parameter we can measure, compare, and perhaps one day engineer. Engineering does not mean building a black hole, but it does mean learning to control timing with gravitational precision. It means treating time dilation as a tool, not only as a curiosity. It also invites a careful question. How far can we push precision before the environment becomes part of the clock? And the deeper twist remains in view. Time can be slowed, warped, and locally frozen in comparison. While the flow we feel may be an emergent story written on top of geometry and entropy, the clocks we build are faithful to physics, yet our intuition is faithful to experience. Between them lies the unsettling possibility that time is not a single thing, but a layered description, local, relational, and, in the deepest regimes, unfinished. We left the black hole with a problem that sounds like poetry, but behaves like engineering. If time can nearly freeze in theory, we must measure that slowing on Earth with disciplined methods. The challenge is not philosophical, and it is not optional, because any claim about time must survive contact with instruments. Precision metrology is the science of measurement at the limits of control and knowledge, where the last decimal place becomes a battlefield. It asks what can be compared, what can be repeated, and what uncertainty remains when you have done everything carefully. In practice, it also asks what the world does to your measurement while you're trying to make it, because the world never stops touching your apparatus. In this chapter, stopping time becomes operational rather than rhetorical, which is where science becomes accountable. We treat time as a variable that can change with motion, gravity, and environment, even when those changes are faint. The phrase becomes a checklist of effects, each one small, each one measurable, and each one waiting to be mistaken for something else. Time is the backbone variable of modern physics because it organizes dynamics, causality, and the meaning of prediction. Without time, equations do not predict change. They merely describe static relationships that never unfold. Time is also the backbone of technology because networks, navigation, and power grids require synchronization that does not drift beyond tolerance. Consider what synchronized really means in a modern city at night, where the glow of windows hides a lattice of timing. Data centers trade timestamps across continents, financial systems order events by microseconds, and cellular towers hand off signals that must arrive in phase. Even the electrical grid depends on frequency coherence, an invisible choreography that collapses if timekeeping becomes sloppy. A clock is not just a device that displays seconds, or a polite accessory to human schedules. A clock is a physical oscillator whose frequency can be compared, transported, and corrected without losing its identity. Every clock is, at its core, a repeating process that can be counted, and the universe supplies many candidates. Historically, we used what we could see and touch, which meant time was tied to the sky and to mechanics. Sundials tracked shadows, water clocks tracked flow, and pendulums tracked gravity's pull on a swinging mass, provided temperature and friction behaved. Then quartz crystals brought electronics into the story, and the tick became a vibration inside a carefully cut piece of rock. Relativity makes a sharp demand on clocks, and it does so without asking permission from engineers. If gravity changes tick rates by height, then clocks become sensors of space-time geometry, not merely keepers of schedule. The clock is no longer merely keeping time inside the world, it is reporting what the world is doing to time. That demand is not abstract, and it does not wait for space missions or extreme experiments. In Einstein's view, proper time is what a clock measures along its own path through space-time, and different paths yield different totals. The moment you build a clock good enough, you are forced to confront that truth in the laboratory. The first modern anchor is the cesium-133 standard, the microwave clock that defined the SI second for decades. It counts 992,670 cycles of a hyperfine transition, which is a quantum tick embedded in atomic structure. That number is not a convention pulled from thin air. It is a commitment to a reproducible quantum event. Cesium's hyperfine transition comes from the interaction between the electron cloud and the nucleus, a tiny magnetic conversation inside the atom. The electron and nucleus behave like coupled magnets, and the energy difference between their alignments sets the microwave frequency. In a beam or fountain clock, cesium atoms are prepared in a known state, interrogated by microwaves, and detected after they respond. In the fountain version, the atoms are tossed upward like a slow-motion spray, then fall back through the microwave field. That flight time lengthens the interrogation, which sharpens the resonance and reduces uncertainty. The second becomes the duration that makes the atoms respond most strongly again and again. Cesium clocks are extraordinary, but they are limited by their oscillation frequency, which sets the scale of their ruler. A microwave wave cycles billions of times per second, yet optics cycles hundreds of trillions, and the difference matters. If you want finer resolution, you do not merely build better electronics, you move to a faster oscillator. Higher frequency oscillations yield finer tick resolution, because each cycle is a smaller slice of time, and smaller slices expose smaller shifts. When you can count more cycles per second, you can resolve smaller fractional changes in the oscillator's rate. It is the difference between measuring a road with mile markers and measuring it with millimeters. There is another advantage hiding inside that frequency increase, and it is about noise rather than speed. Many noise sources scale in ways that make fractional stability easier at higher carrier frequencies if you can control the system. Optics does not magically remove noise, but it gives you a sharper ruler, provided you can keep your hands steady. Optical atomic clocks move the reference transition from microwave to visible or near-visible light, and the payoff is stability. The light is simply the carrier of an oscillation so rapid that it forces the rest of the apparatus to become more disciplined. In the visuals, the story shifts from microwave cavities to gleaming optics, where mirrors and lenses look almost too delicate to define time. The core idea is simple and severe, like a rule written in glass. Lock a laser to an atomic transition, then count the laser's frequency as your time standard. The atom supplies the reference, the laser supplies a usable signal, and feedback control stitches them together. But atoms are not isolated mathematical points, and the lab is not a silent void. They sit in fields, they collide, they move, and they absorb and emit radiation, even when we pretend otherwise. To turn an atom into a clock, you must persuade it to behave like an ideal oscillator, while the rest of the universe tries to disturb it. To do that, the atoms must be protected from everything that scrambles their quantum phase, which is the internal hand of the clock. Temperature, collisions, magnetic fields, and stray light all become timing errors, not mere nuisances. Even the act of measuring the atom can shift it, because probing is itself an interaction. Optical lattice clocks solve this by trapping many atoms in a standing wave of laser light, a trap made from interference. The lattice is a web of light that holds atoms nearly motionless, reducing Doppler shifts and averaging down noise. Visually, it is like an egg carton made of interference fringes, where each well can hold an atom. The standing wave creates periodic intensity peaks, and the atoms are drawn toward those peaks by the dipole force. What looks like empty space becomes structured, because light carries momentum and creates a potential landscape you can engineer. The atoms are not bolted down, but they are confined so tightly that their motion becomes quantized. A common workhorse is strontium, cooled to microkelvin temperatures so Doppler shifts nearly vanish. Ultracold atoms behave like quiet pendulums in a vacuum, with velocities reduced to centimeters per second or less. Their thermal motion becomes so small that for timing purposes, it is almost as if they are hovering. Cooling is not just a convenience, it is an assault on a fundamental error source that hides inside motion. If atoms move, they see the laser frequency shifted by the Doppler effect, and that shift masquerades as a change in time. Laser cooling uses photon momentum to slow atoms step by step, until their velocity distribution collapses. Inside an ultra-high vacuum chamber, the atoms are isolated from collisions that would broaden the transition and destroy coherence. Coherence time becomes a resource that metrology fights to preserve, like a fragile currency. The chamber is not merely empty, it is engineered emptiness, with pressures so low that atoms can wait seconds without meeting an intruder. In a well-lit lab, the vacuum chamber often looks like a small metallic city, built for invisible residents. Stainless steel tubes branch into viewports, pumps hum quietly, and cables wrap around coils and sensors with deliberate symmetry. The clock's heart is hidden behind glass, where the atoms sit in darkness except for carefully shaped beams. The lattice is tuned to a magic wavelength where the trapping light shifts both clock states equally, which is a precise cancellation. That trick cancels a major systematic error while keeping confinement, and it is verified by scanning intensity and watching the frequency stop moving. It is called magic because it feels like cheating, but it is really careful quantum engineering. Light shifts atomic energy levels through the AC Stark effect, and that shift depends on the atomic state and polarization. If the two clock states shift differently, the clock frequency changes with lattice intensity, and stability collapses into a false signal. The magic wavelength is the point where the differential shift vanishes, so the trap holds the atoms without dragging the clock. Now the clock transition can be interrogated with a narrow line-width laser. whose purity becomes part of the time standard. The laser frequency is steered until it sits on the atomic resonance like a needle balancing, sensitive to the slightest push. The feedback loop listens to the atoms, and the atoms, in a sense, discipline the laser. The practical method is a repeated interrogation sequence, and its rhythm becomes the clock's working heartbeat. Prepare the atoms, shine the probe light for a controlled time, then read out how many atoms made the transition. The resulting error signal tells the servo which way to nudge the laser, and the cycle repeats until the lock becomes steady. At this point, the clock is an optical frequency, far too fast to count directly with electronics, and that is a practical crisis. The next tool is the frequency comb, a ruler for light that turns impossible counting into manageable arithmetic. Without it, optical clocks would be exquisite but isolated, like perfect watches sealed inside separate boxes. A frequency comb is a laser that produces a spectrum of evenly spaced lines, each one a stable marker. Each line is a known multiple of a repetition rate that electronics can count, plus a controlled offset that sets the comb's absolute position. In the time domain, it is a train of ultra-short pulses. In the frequency domain, it is a picket fence of colours. The comb's spacing is set by the pulse repetition rate, and the whole comb can slide through frequency space with a controllable offset. By stabilising those parameters, you make every tooth of the comb predictable, and predictability is the currency of metrology. Then, an unknown optical frequency can be measured by beating it against the nearest tooth and counting the difference. This was not a minor incremental invention, and its impact is hard to overstate. The development of optical frequency combs, recognized with a Nobel Prize, turned optical metrology into a practical discipline rather than a heroic stunt. It allowed laboratories to connect optical transitions to the microwave world where counting is easy. The comb links optical frequencies to microwave signals without losing phase information, which is what makes comparisons meaningful. It lets two distant optical clocks be compared as if they shared one reference, even when they sit in different buildings. Phase coherence is the key, because timekeeping is not only about average frequency, but also about the stability of the oscillation's phase over time. With combs, fiber links, and stabilized lasers, timekeeping becomes a networked measurement rather than a single instrument. The laboratory becomes a timing interferometer spanning rooms, buildings, and mountains, and the geometry of cables starts to matter. Every cable becomes suspect, and every vibration becomes a potential source of phase noise. In the visuals, we move from a single vacuum chamber to a wider map of the facility, where timing becomes infrastructure. Fibers snake along trays, disappear through walls, and reappear in adjacent rooms where lasers sit on floating optical tables. Small boxes with blinking indicators hide the fact that they are counting cycles at a rate that dwarfs human intuition. This is where relativity stops being a correction and becomes the signal, which is a conceptual reversal. A clock at one height runs at a measurably different rate than a clock slightly higher, even when both are at rest. The lab, which once tried to eliminate gravity as a nuisance, now uses gravity as the thing being measured. Near Earth, the fractional gravitational redshift is about GdH divided by c squared, and it is the first-order approximation that guides intuition. The formula is small in magnitude, but modern clocks are smaller still in their uncertainty. It tells you that lifting a clock increases its rate, because it sits higher in gravitational potential. The numbers are deceptively gentle, which is why they surprise people who do not live in exponents. With g around 9.8 meters per second squared and c enormous, the effect per meter is roughly 1 part in 10^16. That sounds negligible until your clock's uncertainty approaches 10^18 or 10^9, where negligible becomes a measurable slope. For years, experiments resolved time dilation across centimeters, then across a few millimeters, and each step demanded new discipline. The question became whether time differs across the thickness of a hair, not as philosophy but as data. It is a strange moment when a concept born from stars and high speeds becomes visible on a tabletop. In 2022, groups at NIST and JILA reported gravitational time dilation measured across about a 1 millimeter height difference. Two clocks separated by a millimeter did not agree, even though their lasers, atoms, and models were built for agreement. In ordinary language, they were both correct, and the disagreement was the point. The result is not a metaphor about time flowing uphill, and it is not a trick of interpretation. It is a direct comparison of frequencies that diverge because space-time assigns different proper time rates to different locations. The clocks do not think differently, they simply accumulate phase at different rates because their gravitational potential differs. By 2024, techniques push towards sub-millimeter sensitivity, tightening control of systematics and improving stability over longer averaging times. The laboratory began to see gravity's gradient as a local texture rather than a distant background. What was once a smooth backdrop became a measurable pattern, like faint ridges on a surface you assumed was flat. Physically, the claim is startling and precise, and it changes how the room feels when you look at it. Time differs across a distance you can barely see, even when the room is quiet and still. The air can look calm, the optical table can look rigid, and yet the clocks reveal that the geometry underneath is not uniform. To make such a measurement, you need more than two clocks, because comparison is its own experiment. You need a way to compare them without adding larger errors than the effect you seek, which is a constant danger. That means shared lasers or comb links, careful fiber noise cancellation, and a systematic budget that treats every component as a possible liar. The implication is not that time is broken near Earth, or that our watches are secretly wrong. The implication is that now is not a plane, even on a benchtop, and that simultaneity has structure. Our everyday experience assumes simultaneity is simple, but that assumption is a practical approximation, not a law. If two clocks in the same lab disagree because one is higher by a millimeter, simultaneity becomes a surface with curvature. Our everyday present becomes a warped sheet we approximate as flat, because the warping is ordinarily too small to notice. The better we measure, the more we see that the approximation has edges. This creates narrative tension that the instruments cannot ignore, because improved precision reveals new gradients. The better the clock, the less it can pretend the world is uniform, and the less it can hide behind noise. Each improvement in stability turns a previously invisible gradient into a new signal, and each new signal demands interpretation. At the frontier, the clock is limited not by gears, but by environment and modelling, which must be made explicit. Every systematic shift must be identified, bounded and corrected, and the correction must be justified in public numbers. The work is equal parts physics and bookkeeping, because uncertainty is a number you must defend. Blackbody radiation shifts the transition because ambient thermal photons perturb atomic energy levels, even when no one is shining a beam. Temperature control becomes time control, and thermal design becomes part of the clock's architecture. Even at room temperature, the chamber is bathed in infrared radiation, and the atoms cannot help but feel it. The blackbody shift is subtle because it is not a single photon kicking an atom in an obvious way. It is an average effect of a thermal field, a sea of fluctuating electromagnetic waves with a spectrum set by temperature. Metrologists measure temperatures at multiple points, model gradients, and sometimes build thermal shields so the atoms see a more uniform, radiative environment. Magnetic fields shift levels through the Zeeman effect, and electric fields shift them through Stark effects, which means the room's invisible fields become part of the clock. Shielding and calibration become part of the definition of a second, not an afterthought. A clock is not defined only by an atom, but by the controlled conditions that let the atoms speak clearly. Even the Earth's magnetic field, which feels steady to us, becomes a moving target at this level of sensitivity. Nearby equipment can create stray fields, and currents and cables can add their own signatures that drift with load. Labs wrap chambers in mu-metal shields, drive compensation coils, and map residual fields like cartographers mapping an invisible terrain. Collisions, lattice intensity gradients, and probe-induced shifts all add tiny biases, and each one has its own fingerprint. Metrology turns the lab into a catalogue of small forces that masquerade as time, and the catalogue must be complete. Each effect has a name, a model, and a test designed to reveal whether it is under control. There is also the problem of motion that remains even in a trap, because trapped is not the same as still. Atoms can occupy different vibrational states in the lattice, and residual motion can create time dilation shifts of its own through relativity. The clock must account for relativistic effects inside the apparatus, even when nothing seems to move. When optical clocks report systematic uncertainties near the 10^-19 level, the number is hard to feel, and that is part of the drama. It means a fractional error of 1 part in 10 quintillion, which is beyond ordinary engineering intuition. It also means that almost any ordinary disturbance, heat from a hand, a draft, a tiny vibration, can become a measurable influence. Translate that to human intuition, and it becomes almost absurd, which is why narrators reach for cosmic comparisons. A clock at 10^19 would lose about 1 second over tens of billions of years if it could run undisturbed that long. That is longer than the age of the universe as we currently estimate it, which makes the claim feel like science fiction. That statement is not marketing, it is a way to grasp scale without drowning in zeros. The clock's error over the age of the universe would still be close to a blink, which is the point of the comparison. The deeper truth is that the clock is not perfect, but it is precise enough to reveal imperfections in its surroundings. Such precision changes what a clock is for, and it changes what the Earth looks like to physics. It is no longer only a timekeeper, it is a detector of gravitational potential, and that potential varies with geology. When a clock becomes sensitive to altitude changes of millimeters, it becomes a scientific instrument for Earth itself. This is the opening of relativistic geodesy, sometimes called seeing with time, because the observable is a frequency shift. If gravity changes clock rates, then clocks can map gravity without moving masses or measuring acceleration directly. Instead of measuring how a plumb line tilts, you measure how proper time accumulates. Geodesy has a long history, from surveying with chains and theodolites to satellite missions that map Earth's gravity field. Traditionally, you infer potential from shapes, or from how objects accelerate, or from how satellites orbit in response to mass. Relativistic geodesy adds a new observable frequency. In geodesy, the relevant quantity is gravitational potential, not just height above sea level, which can be misleading. 2 points at the same geometric height can still differ in potential due to mass distribution below and around them. Mountains, aquifers, and dense rock bodies all reshape the potential landscape, even if the surface looks smooth. A clock comparison measures potential differences directly through redshift, which is why the method is so conceptually clean. In principle, it can detect underground structures, aquifers, and density anomalies as timing signatures, provided links and models are stable. The promise is not that a single clock replaces all other methods, but that time becomes a complementary sensor. The Earth becomes a time landscape, with valleys where clocks run slower and ridges where they run faster, and the map is subtle. The map is not drawn in meters, but in frequency ratios that can be compared across distance. The contour lines are not elevations, but equal proper time rates. This also reframes synchronization as a relativistic problem, not merely a communications problem. To synchronize distant clocks, you must account for motion, gravity, signal delays, and path-dependent phase noise that accumulates in links. Even if 2 clocks are identical, the link between them can add fluctuations that mimic drift. Fiber links stabilized against temperature and vibration can carry optical phase over long distances, which turns geography into part of the measurement. They allow continuous comparisons that are far more sensitive than transporting clocks by hand, which introduces motion and downtime. The stabilization works by sending light down the fiber, measuring phase noise, and actively cancelling it in real time. The visuals widen again, from a lab bench to a fiber route that runs under streets and across campuses, like a hidden nervous system. The fiber looks passive, but it is an active measurement path constantly corrected by electronics that never sleep. In a sense, the fiber becomes part of the clock, extending its coherence beyond the room. Now we scale the lab story into a field campaign arc, where precision leaves its protected habitat. Portable optical clocks are leaving the cleanest rooms and heading into messy terrain, where dust and vibration are not theoretical. The question becomes whether the exquisite stability of the lab can survive the vibrations, temperature swings, and power constraints of the real world. Portability is not trivial, because every subsystem resists being moved. Lasers that once lived on floating optical tables must be ruggedized. Vacuum systems must tolerate transport without leaks, and alignment must remain stable after a drive up a mountain road. The clock becomes a piece of expedition equipment, as sensitive as it is powerful. A major target is Mount Blue Sky in Colorado, with comparisons linked back to Boulder through fiber and transportable systems. The altitude difference turns Earth into a controlled gravitational experiment, with an effect large enough to see quickly. The mountain is not just scenery, it is a known change in potential, carved into the landscape. Across a mountain, the predicted redshift is large enough to see quickly, yet small enough to demand careful control of every systematic. The campaign tests general relativity in the regime where technology operates, not in the distant realm of astrophysics. It is a test not of theory's existence, but of our ability to use it reliably. The point is not to prove Einstein again as a slogan, because the theory has already survived a century of scrutiny. The point is to validate timing infrastructure that could support new navigation paradigms, where clocks become field instruments. If you want clocks to serve society outside laboratories, you must show that their accuracy survives deployment. If clocks can measure potential directly, navigation can be built from time rather than from geometry alone, at least in part. A receiver could infer position by reading the gravitationally warped timing field, treating redshift as information. In that view, the world is not only a map of coordinates, but a map of clock rates. This is not a replacement for GPS in the near term, but it is a new layer that changes the failure modes. It offers resilience when signals are jammed, delayed, or unavailable, because local time can carry more authority. It also offers a different kind of truth, because it ties position to physics rather than to a broadcast message alone. Deep space navigation is where the stakes sharpen, because distance turns communication into delay. Far from Earth, radio tracking and ephemerides become limiting, and precise onboard clocks reduce dependence on ground control. When light time delays stretch to minutes or hours, autonomy becomes a necessity rather than a luxury. An optical clock on a spacecraft can timestamp signals, stabilize links, and improve ranging by reducing timing uncertainty at the source. It can also test whether fundamental constants drift over cosmic time, which would appear as slow changes in frequency ratios. Even a tiny drift would appear as a systematic change between different atomic species. Metrology also feeds fundamental physics in quieter ways by turning comparisons into probes of symmetry. Comparing different atomic species probes, possible violations of relativity, new forces, or coupling to dark matter fields that might modulate constants. The logic is simple. If new physics exists, it may shift different transitions by different amounts. If a transient field passes through Earth, it could shift atomic transitions differently in different clocks, and the pattern would matter. A global clock network could become a detector for new physics, not by seeing particles, but by seeing time wobble. The signal would not be a flash of light, but a correlated change in frequency across distant laboratories. All of this pushes toward a looming institutional pivot, where definition catches up to capability. The second is likely to be redefined around 2030 using an optical transition rather than cesium, because the best clocks have moved. The change reflects a deeper truth. The best realization of the second has moved beyond microwaves. Redefinition is not a bureaucratic footnote, it is a change in the world's reference for time, and references shape everything else. It would anchor telecommunications, finance, science, and navigation to optical stability, which reduces long-term drift. It would also reshape calibration chains because national metrology institutes must disseminate time with traceable uncertainty. There is history behind this, because the second has already changed once in spirit, and the change carried cultural weight. Before atomic standards, time was tied to astronomical motion, and Earth's rotation served as the reference for civil time. Atomic time broke that link, because the planet is not as steady as an atom, and modern life demanded better. The challenge is not only building the best clock, but building trust in the unit across borders. The challenge is making clocks comparable across nations, labs, and environments, with agreed uncertainty budgets that survive scrutiny. A second is only a global unit if it can be realized and verified globally. That requires international comparisons, transportable standards, and robust links that do not smuggle in hidden offsets. It requires proving that different optical clocks agree within stated uncertainties, even when they use different atoms and different traps. Agreement is not assumed, because different atoms, different traps, and different models can hide different biases. When the second becomes optical, the old microwave definition becomes a derived approximation, still honoured but no longer primary. The backbone of timekeeping shifts upward in frequency and downward in uncertainty, which changes what must be corrected. The world's timescale becomes more stable, and the corrections become more explicitly relativistic. At that point, the phrase stopping time acquires a sharper meaning, because gradients become visible rather than hypothetical. If we can measure gravitational slowing across millimeters, then time's rate is a field we can chart with instruments. A stoppage is not a dramatic freeze, but a measurable gradient that never fully disappears. The lab becomes a miniature space-time survey, and the visuals can linger on small separations that carry large meaning. Each clock reading is a local statement about how much proper time fits into the surrounding geometry, measured in phase. Two clocks are like two thermometers, except the quantity is not temperature. It is the rate at which reality permits change. Yet the closer we get to perfect measurement, the stranger the concept of a shared present becomes, and the strangeness is earned. Now fractures into local agreements stitched by signals and models, and those stitches have tolerances. Synchronization becomes a negotiated settlement between clocks, links, and relativistic corrections. This is the hidden drama of precision, and it unfolds without spectacle, one digit at a time. Better clocks do not merely improve schedules, they expose that time is not globally uniform even in ordinary places. The revelation is quiet, because it arrives as a small frequency offset, but it is profound. So the chapter's answer is practical, and it is grounded in what the instruments can actually say. We cannot stop time outright on Earth, but we can measure its slowing as a continuous position-dependent effect. We can watch the rate change as we lift a clock, lower it, or carry it across a mountain ridge. We can map the gradient, compare rates, and exploit differences for navigation and science, which turns relativity into a tool. We can treat time as terrain, and the terrain is measurable even when it looks flat. The question becomes not whether time varies, but how finely we can resolve its contours. Yet one question remains, and it points beyond relativity's smooth geometry. If motion and gravity slow clocks by changing space-time intervals, can quantum mechanics freeze change by measurement itself? If observation can alter evolution, then stopping time may have a second meaning. That pivot takes us from better clocks to stranger limits, where the observer becomes part of the dynamics. The next chapter asks whether observation can halt evolution, even when space-time keeps ticking. And if it can, we must ask what kind of time is being stopped: the clock's time or the system's change. We have been bending time with motion and gravity, treating it like a rate that can stretch or compress. Now the story shrinks to the microscopic, where time is tied to change itself, and where change can be negotiated. The visual language shifts with the scale. The wide grid of space-time fades into a clean laboratory bench, and then into a schematic of energy levels. Where relativity gave us clocks in orbit and clocks in valleys, quantum mechanics gives us transitions, phases, and probabilities. Relativity let clocks disagree without any observer touching the clock because geometry does the work. Quantum mechanics adds a sharper claim, and it lands like a whisper that feels too powerful. Observation is not passive bookkeeping. Observation is an interaction that can redirect what happens next. The central question stays the same, but the meaning tightens. According to modern physics, what would it actually mean to stop time, and where does nature allow it? In the quantum world, the closest operational meaning is stopping a system from changing state, holding it in place within its own space of possibilities. In classical physics, a system has properties whether or not we look, and measurement merely reveals them. A planet has a position, a pendulum has an angle, and a clock has a reading, even in darkness. In quantum physics, the state is encoded in a wave function, and that wave function is not a tiny object wearing hidden labels. The wave function is a catalogue of possible outcomes with complex amplitudes, and those amplitudes carry phase as well as magnitude. In plain language, it is not just a list of what might happen, but a rule for how possibilities combine. That phase information is what lets probabilities interfere, cancel, and reinforce like ripples crossing on dark water. Superposition is the key departure from everyday intuition, and it is more precise than the word mixture. A quantum system can be in a combination of distinct possibilities at once, with each possibility weighted by an amplitude. Those possibilities are not ignorance about a hidden answer, they are the state, until measurement forces a definite record. This is why quantum theory feels less like a description of things, and more like a description of allowed changes. It talks about what can be predicted, what can be known, and how predictions update when the world leaves a trace. Even the language of state is a commitment to dynamics, because a state is defined by how it will evolve. Time enters quantum theory through that evolution. Between measurements, the wave function evolves smoothly and deterministically, and the rule is surprisingly rigid. Schrödinger's equation governs that evolution. and it looks like a clockwork law for probability amplitudes, with the Hamiltonian acting as the generator of time translations. The Hamiltonian is not just energy as a number, it is a full operator that encodes the system's structure, fields, couplings, potentials, and the allowed transitions between levels. When the Hamiltonian is stable and isolated, the evolution is unitary, meaning information is preserved within the system's own quantum description. This smooth evolution is not optional interpretation, and it is not a philosophical garnish. It is the engine behind interference patterns, spectroscopy, and the stability of atomic clocks, which count time using extremely sharp quantum transitions. If the wave function did not evolve coherently, quantum technology would not work, and the periodicity of matter would not be so reliable. You can picture it. A beam of atoms passes through a microwave cavity, and their internal states precess like tiny hands on a quantum dial. The phase accumulates, fringes appear, and a frequency emerges with astonishing precision. That precision depends on the very thing measurement seems to threaten: coherent, uninterrupted evolution. But quantum mechanics also contains a second rule, and it is the source of tension that every student eventually meets. Measurement yields a definite outcome, and the result is not a gentle averaging. In the Copenhagen framing, the wave function collapses to an eigenstate consistent with the observed result, and the range of possibilities snaps into a single recorded fact. We do not need to settle every philosophical debate to proceed, because the laboratory gives us a practical definition. Operationally, measurement changes the system, and the change is not optional. The act of extracting information requires coupling to an apparatus, and that coupling perturbs the state, whether we call it collapse or simply entanglement plus decoherence. A measurement is not merely a human glance, and it is not the presence of consciousness in the room. It is any physical interaction that produces an effectively irreversible record in some degree of freedom. A photon scattering from an atom can be a measurement, because the photon carries away which state information. A detector click is a measurement, because it amplifies a microscopic event into a macroscopic trace. Even a strong environmental coupling can act like continuous measurement, because the environment is full of uncontrolled degrees of freedom. Molecules, stray fields, thermal photons, and vibrations can all become a kind of witness. They entangle with the system, and that entanglement spreads information outward until interference becomes practically impossible to recover. This is where the documentary's hook sharpens. What if time is not a river at all, but a switch physics can flip, at least locally, at least for specific changes? In quantum mechanics, the switch is not spacetime geometry. The switch is the rate at which a state is allowed to evolve under repeated interrogation. The chapter's headline effect is the quantum Zeno effect. It is the experimentally verified suppression of transitions by sufficiently frequent measurement, and it is as counterintuitive as it sounds. It is named after Zeno's arrow paradox, where an arrow seems frozen if examined at every instant, never caught in motion. Zeno's ancient argument was philosophical, aimed at the continuity of motion and the meaning of an instant. Yet the name fits because quantum theory turns the metaphor into a calculation with knobs you can turn. The paradox becomes a protocol: measure, reset, measure again, and watch change hesitate. In 1977, Baidyanath Misra and George Sudarshan formalized the idea with the tools of modern quantum theory. They showed that in the limit of continuous observation, an unstable quantum system can be prevented from decaying. The system is held near its initial state by the measurement process itself, not by a physical barrier in space. Their work arrived in a period when quantum foundations were being re-examined with new seriousness. The mathematics of open systems, decoherence, and measurement theory was maturing, and experiments were becoming clean enough to test subtle predictions. The Zeno effect sat at the intersection, half conceptual provocation, half operational recipe. The claim sounds like a trick, so we ground it in the structure of quantum dynamics rather than in slogans. The key is what happens at very short times before the familiar exponential law takes over. For many systems, the survival probability does not start with simple exponential decay, and that first moment matters. At very short times, the survival probability is approximately quadratic in time, not linear. That quadratic behavior is a direct consequence of unitary evolution and the expansion of the time evolution operator. In plain terms, the system initially leaves its starting state slowly, in a way that can be interrupted. The intuition is subtle but vivid. A classical decay can begin immediately, like sand slipping through fingers at a steady rate. A quantum transition begins with a kind of hesitation, because probability must be built from amplitudes, and amplitudes change smoothly. The earliest departure is gentle, and that gentleness is the opening the Zeno effect exploits. Mathematically, the short-time expansion of the evolution operator produces a leading correction that scales with the energy uncertainty of the initial state. If the state has a spread of energies under the Hamiltonian, it has room to evolve away. That spread sets a characteristic Zeno time, a timescale within which the quadratic approximation holds. If you measure once after a short interval, you project the state back onto the initial subspace with high probability. If you measure again after another short interval, you repeat the reset, and the system begins again from near the same starting line. With enough measurements, the cumulative probability of leaving can be strongly reduced, even though the Hamiltonian is still trying to drive change. The guardrail analogy helps, but it must be handled carefully, because metaphors can smuggle in the wrong physics. Imagine a system trying to move from one lane to another on a highway. If you keep forcing it back into the original lane, it cannot complete the transition, and the journey becomes a series of aborted swerves. But analogies can mislead if they imply a conscious watcher or a classical shove. The real mechanism is quantum projection combined with short-time dynamics, and it is indifferent to human intent. The measurement does not scare the system. It changes the state by entangling it with a measuring device, then conditioning on an outcome that becomes a record. In the simplest mathematical picture, start in an initial state and let the system evolve for a small time dt under a Hamiltonian. The overlap with the initial state remains close to 1, with a deviation that scales like d10 or stu. That scaling is the crucial detail because it means the first step away is smaller than you might expect. Now measure whether the system is still in the initial state. If it is, the state is projected back, and the clock for leaving effectively restarts, because the state is restored within that measured subspace. Repeat n times over a fixed total time t, with dt equal to t divided by n, and the departure is sliced into many tiny hesitant attempts. As n increases, the probability of remaining approaches 1, within the assumptions of ideal projective measurement and perfect selectivity. The limit is not magic, and it does not violate the Schrödinger equation. It is the consequence of repeatedly sampling a regime where departure is only quadratic, then repeatedly re-preparing the same condition. There is an important nuance hiding in that word ideal. Real measurements take time, have finite strength, and may not perfectly distinguish states, so the freeze is never absolute. Yet the principle survives, because the essential ingredient is not perfection. The essential ingredient is that information extraction, when frequent enough, reshapes the effective dynamics. This is the first major narrative beat. In relativity, time dilation is passive and the universe does it to you without asking. You place a clock in motion or gravity, and the clock accumulates less proper time without anyone intervening. The clock still ticks locally, but its total tick count differs when paths reunite. In the quantum Zeno effect, the slowing is active, and it depends on interaction. It depends on information extraction, and the physical coupling that makes that extraction possible. The stoppage is not a coordinate artifact, and it is not a trick of perspective. It is a change in dynamical behavior caused by measurement back action. The next beat is accountability, because physics demands more than a clever story. If this were only philosophy, it would not belong in a documentary about stopping time. The quantum Zeno effect is not a metaphor, and it is not confined to thought experiments. It is a laboratory result with quantitative signatures, measured in populations, rates, and decoherence times. The canonical early experiment is Itano, Heinzen, Bollinger, and Wineland in 1990, carried out with the precision culture of ion trapping. They used trapped beryllium ions and drove transitions between internal states, treating each ion like a controllable quantum system. Then they applied frequent measurement pulses designed to check whether the ions had changed state, and they watched the transition slow. The setup is conceptually clean, which is why it became a landmark. Prepare the ions in an initial state, often a well-defined hyperfine or electronic level. Apply a resonant drive that would normally produce Rabi oscillations, moving population between states like a pendulum in Hilbert space. Insert measurement interactions at a controllable rate, and compare the outcome to the uninterrupted case. Rabi oscillations are a perfect stage for this drama, because they are coherent and reversible. Left alone, the system does not simply decay, It swings between states with a frequency set by the drive strength. That makes any suppression unmistakable, because the expected motion is rhythmic, predictable, and easy to quantify. In the experiment, the measurement was not a mystical act, but a physical protocol using light. Optical pumping and scattering processes created state-dependent signals, and scattered photons carried away information about which state the ion occupied. That photon leakage is exactly what turns a quantum superposition into a classical record, because the environment now has a distinguishable imprint. As the measurement rate increases, the driven transition is suppressed, and the system remains closer to the initial state than it would under uninterrupted Schrödinger evolution. The suppression scales with how frequently the system is interrogated, consistent with the Zeno prediction, and it can be plotted as a clear deviation from the expected oscillation amplitude. This experiment matters for two reasons, and both cut to the documentary's theme. It shows that measurement is not a mere readout at the end, like checking a stopwatch after the race. It shows that the measurement schedule can reshape the trajectory, even when the Hamiltonian drive is held fixed, as if the act of checking becomes part of the engine. It also forces a careful definition of measurement in practice, because the word can hide many mechanisms. In the Atano experiment, the measurement pulses cause decoherence in the measured basis, effectively destroying the phase relations needed for the transition to proceed coherently. The watching was implemented through physical interactions that made alternative histories distinguishable, and distinguishability is the enemy of interference. This is where the story becomes more precise and more unsettling. Watching means coupling, and coupling means disturbance, even when the disturbance is gentle. The Zeno effect is not free, and it is not a loophole that lets you freeze without consequences. It trades coherent evolution for information and defacing, and that trade has a thermodynamic shadow. To see that shadow, imagine the apparatus as a chain of amplifiers. A microscopic difference in state becomes a macroscopic difference in detector response. And that macroscopic difference is stable because it is dissipative. The record persists because energy has been spent to make two outcomes separable, and that separability is what makes the measurement effectively irreversible. The next beat is differentiation, because Zeno is not the only possible outcome of frequent intervention. Under some conditions, measurement can accelerate transitions or decay, and the same basic logic can flip direction. This is called the anti-Zeno effect, and it reminds us that nature does not reward simplistic slogans. The difference is not a contradiction, and it is not an escape from quantum theory. It depends on the system's spectral density, the measurement bandwidth, and how the measurement modifies the environment seen by the system. Frequent interventions can either inhibit or enhance escape, depending on what timescales and couplings dominate, and on whether the measurement effectively broadens the system's energy distribution. In other words, the act of monitoring can reshape the effective decay channels. If the measurement couples the system to modes that facilitate transitions, it can open doors rather than close them. If it repeatedly projects onto a subspace where short-time departure is suppressed, it can lock the system in place. The same tool can be a brake or an accelerator, depending on how it is built. For our central theme, we keep the headline on freezing, because it is the clearest operational sense in which change can be held back. The Zeno regime is not a global stoppage of spacetime, and it does not imply the universe pauses. It is a local stoppage of state evolution, a refusal of a particular transition to complete under persistent interrogation. We also clarify what is not being claimed, because precision is part of the suspense. The Zeno effect does not stop the laboratory clock, and it does not halt the passage of proper time in the relativistic sense. It stops a particular transition from occurring with high probability by repeatedly projecting onto a subspace or by enforcing strong continuous coupling. This distinction is the chapter's spine, and it keeps the story honest. Relativity changes how much time accumulates along a world line, and it does so even if no one looks. Quantum Zeno changes whether a system's state is allowed to depart from its starting condition, given repeated measurement, and that change depends on the monitoring protocol. If relativity is a story about paths through space-time, Quantum Zeno is a story about paths through Hilbert space. One path is drawn on a cosmic stage of geometry and gravity. The other is drawn in an abstract space of amplitudes, where distance is overlap and motion is phase rotation. Yet both stories ask what it means for change to be slowed, and both insist on operational definitions. Now we connect to technology. because the documentary's promise is consequences, not curiosities. Quantum devices are fragile because of decoherence, and fragility is not a moral weakness. Decoherence is the loss of phase coherence due to uncontrolled coupling with the environment, which effectively performs measurements you did not ask for. A qubit is a controlled two-level system, and it can be realized in many physical forms. It might be an ion's internal states, a superconducting circuit's energy levels, a spin in a crystal defect, or a photon's polarization. Its power comes from superposition and entanglement, because amplitudes can interfere and correlations can exceed classical limits. Its weakness is that the environment effectively measures it, collapsing superpositions into classical mixtures and destroying quantum information. A stray photon, a fluctuating electric field, or a vibrating substrate can become a witness. Once the environment carries away which state information, the qubit's phase is no longer private, and the computation loses its quantum advantage. At first glance, the Zeno effect sounds like it would make decoherence worse, because it involves measurement and dephasing. The practical twist is that controlled measurement can sometimes protect information better than uncontrolled noise, because control lets you choose what is being measured. If you can force the system to reveal the right information, you can prevent it from leaking the wrong information. One application is error suppression, by confining dynamics to a protected subspace, a region of Hilbert space designed to encode information redundantly. If you continuously measure a stabilizer or a conserved quantity, you can inhibit transitions that would take the system out of the code space. The measurement acts like a constraint that pins the system's evolution, not by adding energy barriers, but by enforcing informational boundaries. Another application is continuous measurement combined with feedback, which turns observation into a control loop. You monitor a qubit weekly, infer its state in real time, and apply control pulses to counteract drift or correct errors. The measurement does not merely collapse, it provides a signal for stabilization, like a pilot using instruments to hold a course through turbulence. In modern quantum control, measurement often means weak, continuous monitoring rather than sharp projective collapse, and that distinction matters for realism. Weak measurement extracts partial information while adding partial disturbance, and the state update becomes gradual. The Zeno effect has a generalized form in this regime, because strong continuous coupling can create Zeno subspaces, where certain transitions are dynamically forbidden. This is sometimes described as dynamical superselection, and the phrase is technical, but the idea is intuitive. The system's Hilbert space is partitioned by the measurement interaction, and evolution between partitions is suppressed. The result is not mystical, and it is not a new law of nature. It is a consequence of strong coupling and rapid dephasing in a chosen basis, which makes coherence between partitions vanish before it can do work. The engineering consequence is clear, and it has become part of the language of quantum hardware. If you can choose what the environment effectively measures, you can choose what gets frozen. That is a route to stabilizing qubits, maintaining entanglement, and extending coherence times in practical devices where every extra microsecond can be a victory. Yet the mysterious tone returns when we step back from the circuit diagrams and pulse sequences. In relativity, the universe slows your clock without asking your permission, and the effect is written into geometry. In quantum mechanics, you can slow a system's change by insisting on information, again and again, as if curiosity itself becomes a physical force. This creates a philosophical tension that is also a physical one, and it is not easily dissolved. Relativistic time dilation is about geometry and motion, and it is indifferent to knowledge. Quantum Zeno is about interaction and information, and it depends on what is being monitored, what basis is privileged, and what counts as a record. So what does it mean to stop time, according to physics, in this quantum chapter? It means preventing evolution in a chosen basis by repeated measurement or strong continuous coupling, and it means doing so in a way that can be counted and tested. It means turning change into a conditional statement, dependent on interrogation and dependent on the structure of short-time quantum dynamics. But the chapter must also acknowledge the limits, because the limits are where the next chapter is hiding. Perfect freezing requires idealized measurements and infinite rate, which no real apparatus achieves. Real measurements have finite strength, finite duration, and added noise, and those details determine how strong the inhibition can be, and whether the system slips into anti-Zeno acceleration instead. There is also a cost in energy, entropy and disturbance, even when the measurement is engineered with care. Measurement requires an apparatus that ends in distinguishable states, and distinguishability is tied to irreversibility and amplification. Ultimately, the record is stable because something has been dissipated, and dissipation is the signature of thermodynamic expense. You can feel the bridge forming. If quantum observation can freeze evolution locally, why does time feel relentlessly one way in the macroscopic world, where everything is constantly interacting? Why does the world not look Zeno-frozen, even though it is made of quantum parts, and even though the environment is always watching in some sense? The transition is not a change of subject, and it is not a retreat from quantum mystery. It is the next layer of the same question, now scaled up to the world of heat, friction, and irreversible records. The arrow of time is not explained by relativity's geometry alone, and it is not explained by quantum measurement alone, because both still leave open the question of why the future feels different from the past. We end with a forward pull, and we keep the claim grounded. The quantum Zeno effect shows that change can be inhibited by observation, in a way that is real and measurable, and in a way that forces us to treat information as physical. Now we must ask how observation, irreversibility, and entropy conspire to make time feel like a one-way switch, even when the microscopic laws look reversible. Enter thermodynamics and the arrow of time. We have been bending time with motion and gravity, treating it like a rate that can be tuned by the universe itself. Now the story narrows to the microscopic, where time is not read from gears or orbits. Here, time is tied to change, and change is tied to what can be known. The camera that once floated past planets and pulsars now glides into a vacuum chamber. Metal walls gleam under cold light, and cables feed signals into quiet racks of electronics. Behind a window of glass, a trap holds a handful of ions in place, and the world becomes a choreography of pulses. Relativity let clocks disagree without any observer touching the clock, because space-time geometry sets the pace. Quantum mechanics adds a sharper claim, and it feels almost personal. Observation is not passive bookkeeping. Observation is an interaction that can redirect what happens next, even when the observer is just a photodiode. The central question stays the same, but the definition becomes operational. According to modern physics, what would it actually mean to stop time, and where does nature allow it? In the quantum world, the closest meaning is stopping a system from changing state, preventing the transition that would otherwise occur. In classical physics, a system has properties whether or not we look, and measurement reveals a pre-existing value. A coin is heads or tails, a pendulum has an angle, and a planet has a trajectory, even if no one records it. In quantum physics, the state is encoded in a wave function, and the wave function is not a picture of a tiny object with hidden coordinates. The wave function is a catalogue of possible outcomes with complex amplitudes, and complexity here is literal. The amplitudes are complex numbers, and their phases can matter as much as their magnitudes, because phases decide how possibilities interfere. In plain language, the wave function is a rule for predicting what records can appear, and how likely each record is. Superposition is the key departure from everyday intuition, and it is the reason quantum theory can feel like a different kind of realism. A quantum system can be in a combination of distinct possibilities at once, and the combination is not a lack of knowledge. Those possibilities are the state, until measurement forces a definite record, and the record becomes part of the world. Time enters quantum theory through dynamics, and dynamics is where the wave function earns its keep. Between measurements, the wave function evolves smoothly and deterministically, and the rule is compact enough to fit on a chalkboard. Schrödinger's equation governs that evolution, and it looks like a clockwork law for probability amplitudes, with the Hamiltonian setting the rhythm. The Hamiltonian is the system's generator of change, and it encodes the energies and couplings that make transitions possible. It tells the state how to rotate in its abstract space, and it does so without randomness. Randomness enters when we ask a question that demands a definite answer, because the answer must be one of the allowed outcomes. This smooth evolution is not optional interpretation. It is the engine behind interference, spectroscopy, and the stability of atomic clocks, which are among the most accurate timekeepers ever built. If the wave function did not evolve coherently, the sharpness of spectral lines would blur, and the precision of frequency standards would collapse. But quantum mechanics also contains a second rule, and it is the source of the theory's famous tension. Measurement yields a definite outcome, and the outcome is not merely revealed. In the Copenhagen framing, the wave function collapses to an eigenstate consistent with the observed result, and the other possibilities are removed from the description. We do not need to settle every philosophical debate to proceed, because the laboratory offers a working definition. Operationally, measurement changes the system, and the change is unavoidable. The act of extracting information requires coupling to an apparatus, and that coupling perturbs the state, whether we describe it as collapse or entanglement with a macroscopic record. A measurement is not merely a human glance. It is any physical interaction that produces an irreversible record in some degree of freedom, and irreversible here means practically unrecoverable. A photon scattering from an atom can be a measurement, because the photon carries away information about the atom's state. A detector click is a measurement, because it amplifies a microscopic event into a stable, macroscopic trace. A strong environmental coupling can act like continuous measurement, and this is where the world outside the lab becomes relevant. The environment is full of degrees of freedom, and they are always ready to become witnesses. When they do, coherence leaks away, and what was once a superposition becomes a mixture that behaves classically. This is where the documentary's hook sharpens into a claim you can test. What if time is not a river at all, but a switch physics can flip, at least for a chosen process? In quantum mechanics, the switch is not space-time geometry. The switch is the rate at which a state is allowed to evolve under repeated interrogation, and the interrogation is physical. The chapter's headline effect is the quantum Zeno effect, and it is as dramatic as its name. It is the experimentally verified suppression of transitions by sufficiently frequent measurement. It is named after Zeno's arrow paradox, where an arrow seems frozen if examined at every instant, never caught in motion. Zeno's paradox was a meditation on continuity, and it haunted thinkers long before calculus made motion mathematically tame. Quantum theory revives the mood because it makes examined at every instant a meaningful limit. The paradox becomes an experimental question. How often can you ask before the system stops answering with change? In 1977, Baidyanath Misra and George Sudarshan formalized the idea with careful mathematics. They showed that in the limit of continuous observation, an unstable quantum system can be prevented from decaying, held near its initial state by the measurement process itself. Their result was not a loophole in physics, but a consequence of how quantum probabilities begin. The claim sounds like a trick, so we ground it in the structure of quantum dynamics. The key is what happens at very short times, where intuition built from exponential decay can fail. For many systems, the survival probability does not start with a simple exponential, and that early time behavior is the lever. At very short times, the survival probability is approximately quadratic in time, and this is not an arbitrary assumption. That quadratic behavior follows from unitary evolution and the Taylor expansion of the time evolution operator. It means the system initially leaves its starting state slowly, and that slow start can be interrupted. The quadratic law is tied to energy uncertainty, because a perfectly sharp energy eigenstate would not evolve into a different state at all. If the initial state is a superposition of energies, phases accumulate at different rates, and the state begins to rotate away. The broader the energy spread, the shorter the timescale over which the state noticeably changes. If you measure once after a short interval, you project the state back onto the initial subspace with high probability. If you measure again after another short interval, you repeat the reset, and the system begins again from nearly the same condition. With enough measurements, the cumulative probability of leaving can be strongly reduced, and the transition can be effectively frozen. The guardrail analogy helps, but it must be handled carefully. Imagine a system trying to move from one lane to another, guided by its Hamiltonian like a steering input. If you keep forcing it back into the original lane, it cannot complete the transition, and the attempt becomes a stutter. But analogies can mislead if they imply a conscious watcher or a classical shove. The real mechanism is quantum projection combined with short-time dynamics, and it is indifferent to intention. The measurement does not scare the system. It changes the state by entangling it with a measuring device, then conditioning on an outcome that becomes a record. In the simplest mathematical picture, start in an initial state, and let the system evolve for a small time bit under a Hamiltonian. The overlap with the initial state remains close to 1, with a deviation that scales like d to c, 2, and that scaling is the entire trick. It tells you that if you cut time into enough slices, each slice is too short for much departure. Now measure whether the system is still in the initial state. If it is, the state is projected back, and the clock for leaving effectively restarts. Repeat n times over a fixed total time t, with dt equal to t divided by n, and the system is repeatedly returned to the same starting region. As n increases, the probability of remaining approaches 1, within the assumptions of ideal projective measurement. The limit is not magic, and it is not a violation of conservation laws. It is the consequence of repeatedly sampling a regime where departure is only quadratic, then repeatedly conditioning the state on survival. This is the first major narrative beat, and it mirrors the earlier chapters in a new register. In Relativity, time dilation is passive because geometry does the work. You place a clock in motion or gravity, and it accumulates less proper time without anyone intervening, and the effect is universal. In the quantum Zeno effect, the slowing is active and it depends on information extraction. It depends on the coupling that makes that extraction possible, and that coupling is part of the system's physics. The stoppage is not a coordinate artifact. It is a change in dynamical behavior caused by measurement back action, and it can be tuned. The next beat is accountability, because a documentary about physics must pay its debts in data. If this were only philosophy, it would not belong here. The quantum Zeno effect is not a metaphor, and it is not a poetic label for indecision. It is a laboratory result with quantitative signatures, measured in populations and transition rates. The canonical early experiment is Itano, Heinzen, Bollinger, and Wineland in 1990. They used trapped beryllium ions, held in place by electromagnetic fields, and drove transitions between internal states with carefully timed pulses. Then they applied frequent measurement pulses designed to check whether the ions had changed state, and the transition slowed as predicted. The setup is conceptually clean, and the cleanliness matters because it isolates the effect. Prepare the ions in an initial state, and apply a resonant drive that would normally produce Rabi oscillations, swinging population between states. Insert measurement interactions at a controllable rate, and you can watch the oscillation's amplitude shrink. The measurement was implemented through optical pumping and scattering processes that created state-dependent signals. Scattered photons carried away information, and that information destroyed coherence in the measured basis. In effect, the experiment engineered a controlled environment that looked at the ion at chosen times, rather than letting uncontrolled noise do it continuously. As the measurement rate increases, the driven transition is suppressed, and the system remains closer to the initial state than it would under uninterrupted Schrödinger evolution. The suppression scales with how frequently the system is interrogated, consistent with the Zeno prediction, and the plots show the difference with stark clarity. This experiment matters for two reasons. It shows that measurement is not a mere readout at the end, because the act of checking changes what happens next. It shows that the measurement schedule can reshape the trajectory, even when the Hamiltonian drive is held fixed, as if information itself becomes a control parameter. It also forces a careful definition of measurement in practice, because the word covers a spectrum of interactions. The Itano experiment used physical processes that decohere superpositions in the measured basis, making the alternatives distinguishable. That distinguishability is what blocks interference, and interference is what allows coherent transitions to proceed smoothly. This is where the story becomes more unsettling, because it reveals a cost. Watching means coupling, and coupling means disturbance, even when the disturbance is engineered. The Zeno effect is not free. It trades coherent evolution for information and dephasing, and it turns the act of making a record into a dynamical constraint. The next beat is differentiation, because not all frequent interventions produce freezing. Under some conditions, measurement can accelerate transitions or decay, and the same logic can flip. This is called the anti-Zeno effect, and it depends on the system's spectral density, the measurement bandwidth, and how monitoring reshapes the effective environment. The difference is not a contradiction, and it does not undermine the Zeno story. It reminds us that measurement is not a single operation, but a family of couplings with different timescales and strengths. Frequent interventions can either inhibit or enhance escape, depending on what processes they amplify or suppress. For our central theme, we keep the headline on freezing, because it is the clearest operational sense in which change can be held back. The Zeno regime is a local stoppage of state evolution, not a global stoppage of space-time. It is the refusal of a particular transition to complete, enforced by a repeated projection, or strong continuous coupling. We also clarify what is not being claimed, because the boundary matters. The Zeno effect does not stop the laboratory clock, and it does not halt the passage of proper time. It stops a particular transition from occurring with high probability by repeatedly projecting onto a subspace, and the rest of the world continues. This distinction is the chapter's spine. Relativity changes how much time accumulates along a world line, and it is indifferent to knowledge. Quantum Zeno changes whether a system's state is allowed to depart from its starting condition, given repeated measurement, and it depends on what is being monitored and how. Now, we connect technology, because the consequences are already shaping the future. Quantum devices are fragile because of decoherence, which is the loss of phase coherence due to uncontrolled coupling with the environment. Decoherence is what makes quantum behavior fade into classical behavior, not by adding friction, but by leaking information. A qubit is a controlled two-level system, and its power comes from superposition and entanglement. Its weakness is that the environment effectively measures it, collapsing superpositions into classical mixtures and destroying quantum information. In practice, the environment can be 1,000 small witnesses, each taking a tiny piece of the phase. At first glance, the Zeno effect sounds like it would make decoherence worse, because it involves measurement and dephasing. The practical twist is that controlled measurement can sometimes protect information better than uncontrolled noise, because it lets engineers choose the basis and the constraint. A controlled constraint can be safer than an uncontrolled leak. One application is error suppression by confining dynamics to a protected subspace. If you continuously measure a stabilizer or a conserved quantity, you can inhibit transitions that would take the system out of the code space. The measurement acts like a constraint that pins the system's evolution, and the pinning is informational rather than mechanical. Another application is continuous measurement combined with feedback, which turns observation into a stabilizing loop. You monitor a qubit weekly, infer its state in real time, and apply control pulses to counteract drift or correct errors. The measurement does not merely collapse, it provides a signal, and the signal becomes a handle. In modern quantum control, measurement often means weak, continuous monitoring rather than sharp projective collapse. The Zeno effect has a generalized form in this regime, because strong continuous coupling can create Zeno subspaces where certain transitions are dynamically forbidden. The system is not frozen in all respects, but it is fenced in. This is sometimes described as dynamical superselection. The system's Hilbert space is partitioned by the measurement interaction, and evolution between partitions is suppressed, because coherence between them is destroyed faster than it can build. The result is not mystical. It is a consequence of strong coupling and rapid dephasing in a chosen basis. The engineering consequence is clear. If you can choose what the environment effectively measures, you can choose what gets frozen, and that choice can protect fragile quantum information. That is a route to stabilizing qubits, maintaining entanglement, and extending coherence times, which is the currency of quantum computation. We keep the mysterious tone by returning to the broader question. In relativity, the universe slows your clock without asking your permission, and the cause is geometry. In quantum mechanics, you can slow a system's change by insisting on information, again and again, and the cause is interaction. This creates a philosophical tension that is also a physical one. Relativistic time dilation is about geometry and motion, and it is indifferent to knowledge. Quantum Zeno is about interaction and information, and it depends on what is being monitored, what counts as a record, and what basis becomes privileged. So what does it mean to stop time, according to physics, in this quantum chapter? It means preventing evolution in a chosen basis by repeated measurement or strong continuous coupling. It means turning change into a conditional statement, dependent on interrogation and dependent on the short-time structure of quantum dynamics. But the chapter must also acknowledge the limits, because limits are where the next question begins. Perfect freezing requires idealized measurements and infinite rate, which no real apparatus achieves. Real measurements have finite strength, finite duration, and added noise, and those details determine how strong the inhibition can be. There is also a cost in energy, entropy, and disturbance. Measurement requires an apparatus that ends in distinguishable states, and that distinguishability is tied to irreversibility and amplification. Ultimately, the record is stable because something has been dissipated, and dissipation points toward thermodynamics. This is the bridge to the next chapter's domain. If quantum observation can freeze evolution locally, why does time feel relentlessly one way in the macroscopic world, where records accumulate everywhere? Why does the world not look xeno-frozen, even though it is made of quantum parts, and even though the environment is always interacting? The transition is not a change of subject. It is the next layer of the same question, now scaled up to the world of heat, friction, and entropy. The arrow of time is not explained by relativity's geometry alone, and it is not explained by quantum measurement alone, because both still leave open the mystery of irreversibility. We end with a forward pull. The quantum Zeno effect shows that change can be inhibited by observation, in a way that is real and measurable, and in a way that makes information feel physical. Now we must ask how observation, irreversibility, and entropy conspire to make time feel like a one-way switch. Enter thermodynamics and the arrow of time. We have slowed time with motion, warped it with gravity, and stalled change with measurement. Yet the deepest mystery remains. Most fundamental equations barely notice time's direction. In the clean world of idealized laws, the future does not look privileged over the past, because the mathematics often permits both directions with equal ease. Newton's laws run forward and backward if you reverse every velocity, and the same trajectories reappear as if nothing happened. In a time-reversed film of two billiard balls colliding, the contact point still obeys the same conservation laws. Energy and momentum do not complain. Maxwell's equations mostly cooperate as well, provided you reverse currents and fields in the consistent way that preserves their symmetries. Electric and magnetic fields interlock through changing flux, and that coupling is indifferent to our sense of earlier and later when the reversals are applied correctly. Even the waves of light, so fast they feel like pure now, do not inherently prefer a direction, because the wave equation admits solutions that propagate either way. Schrödinger's equation is time reversal symmetric for isolated systems, and unitary evolution keeps information intact. The complex phase of a wave function rotates smoothly, and the rule that moves it forward can be inverted in principle. In that mathematical sense, tomorrow is as permissible as yesterday, and the equations do not flinch. Yet our experience is lopsided, and it is lopsided everywhere, from kitchens to galaxies. We remember the past but not the future, and we can replay yesterday in our minds while tomorrow remains blank. We feel anticipation, but we do not feel recollection of what has not happened, and a symmetry so intimate it seems built into consciousness. Broken cups do not reassemble, and ashes do not become logs, even though atoms obey reversible rules. A splash does not leap back into a glass, and perfume does not retreat into its bottle, even though each molecule is still following ordinary mechanics. Every record points one way: photographs, fossils, hard drives, and the faint afterglow of distant starlight. So what is the missing ingredient? The one that turns reversible laws into irreversible stories? The answer is not hidden in a new force, but in a new kind of reasoning. Statistical reasoning applied to enormous numbers. It is a shift in viewpoint, from tracking exact trajectories to counting the overwhelming majority of possibilities. Thermodynamics enters as the hidden engine behind direction. It does not rewrite microscopic laws, and it does not add a special forward time term to the equations. Instead, it tells us what almost always happens when we stop pretending we can follow every microscopic detail. Instead, it explains why macroscopic histories overwhelmingly flow one way, because probability crushes the alternatives. The arrow appears when we stop tracking every detail and start talking in summaries, the way real observers must. The price of practical description is that we compress reality, and compression hides the special correlations that reversal would require. Start with a claim that sounds like a metaphor but is actually a definition. Entropy measures multiplicity, the number of microstates compatible with a macrostate we can describe. In Boltzmann's language, it is tied to counting, and in modern terms, it is tied to information we do not possess. A macrostate is what we can see and summarize, like pressure, temperature, density, or the smooth outline of a cup. It is the language of thermometers, barometers, and everyday observation, where we describe a system with a handful of numbers. A macrostate is also what engineering relies on, because no design document lists the position of every atom. A microstate is the full specification of the system's underlying degrees of freedom. In classical terms, it is every position and momentum. In quantum terms, it is the full wave function or density matrix. It includes the fine-grained correlations between parts, the hidden synchrony that can make a state unusually special. Many microstates can look identical at the macroscopic level, because our coarse description ignores most details. Entropy counts how many invisible arrangements hide beneath the same visible description, and that count grows explosively with system size. When you hear astronomically large, thermodynamics often means vastly larger than astronomy. When multiplicity is large, entropy is high, and when multiplicity is small, entropy is low. The second law then becomes a statistical statement about what happens next, not a magical prohibition. It says that systems move from rare descriptions to common ones, because there are simply more ways to be common. To make that statement concrete, imagine a gas in a box. One macrostate might be uniform density and temperature, while another might be all molecules crowded into one corner. Both macrostates are allowed by mechanics, and both can be written into the same equations, but they are not equally represented among microstates. The crowded corner corresponds to an astronomically tiny fraction of possible molecular arrangements, because each molecule must agree to be in the same region. Uniformity, by contrast, is compatible with an immense range of microscopic placements and momenta. If you start in a low-entropy macrostate, there are vastly more nearby high-entropy macrostates than low-entropy ones. Random microscopic motion will almost certainly push you toward the larger set, because there are simply more ways to be there. The system does not aim for disorder, it wanders, and the combinatorics bias the wandering. The drift is not moral, and it is not mystical. It is combinatorics amplified by huge numbers. With roughly 1023 particles, the counting becomes so extreme that almost certainly becomes effectively inevitable. The probability of a spontaneous return to a special arrangement becomes so small that it is meaningless on human timescales. This is why disorder is statistically favoured, even when every particle follows reversible dynamics. Reversibility at the micro level does not imply reversibility at the macro level, because the macro description throws away information. When we say the gas is uniform, we have already decided not to care which molecule is where. That missing information is not decorative. It is the difference between a reversible movie and a one-way story. If you cannot specify the correlations between particles, you cannot reconstruct the past from the present. The present can be compatible with countless different pasts, and thermodynamics tells you which pasts are typical. Coarse graining is the quiet step that makes the arrow visible. We describe gases with a few variables, not with every molecule's trajectory, and that compression is the price of practical knowledge. In effect, we trade microscopic certainty for macroscopic predictability, and the arrow appears in that trade. In a real laboratory, we never know the exact microstate, and we never control it perfectly. The environment, air molecules, photons, vibrations, constantly entangles with the system and spreads information outward. Even in classical language, tiny perturbations leak in and scramble the delicate coordination reversal would demand. That spreading is crucial, because it turns microscopic details into inaccessible correlations. The information is not necessarily destroyed in the deepest quantum sense, but it becomes unusable for reversal. It is like ink diffusing in water, still present, still conserved in principle, yet practically unrecoverable without impossible precision. A cup shatters because there are more microstates that look like shards than microstates that look like a cup. The reverse is not forbidden by mechanics, but it is so improbable that the universe will not wait. The floor, the air, and the vibrations in the room all participate, quietly absorbing the correlations that would have to be unabsorbed. To see the scale of the improbability, picture every shard leaping from the floor and assembling mid-air into a seamless ceramic shell. The required microstate would demand exquisitely tuned velocities and phases, coordinated down to molecular vibrations. Even the sound waves that left the impact would have to converge back into the cup, an acoustic miracle that would announce its own impossibility. Irreversibility is then a story about typicality. Typical microstates consistent with a macrostate evolve toward macrostates with higher multiplicity, while the time-reverse trajectory exists only for atypical states prepared with extraordinary precision. The equations allow the reversal, but the universe almost never supplies the preparation. The second law becomes a law because we never prepare those correlations. We do not know how, and even if we did, the environment would scramble them faster than we could protect them. The more degrees of freedom you include, the more places there are for the needed coordination to leak away. This is why the arrow feels absolute, even though it emerges from statistics. The world's default is to erase the fine details that reversal would demand, and it does so relentlessly. The arrow is not a commandment, it is the outcome of typical states in a world we can only observe coarsely. Historically, this was not obvious, and it took decades of debate to clarify. Boltzmann's statistical view of entropy clashed with the reversible elegance of mechanics, and critics raised sharp paradoxes about why entropy should rise at all. The argument was not merely technical, it was philosophical, because it forced physics to confront probability as a physical tool. Loschmidt pointed out that if microscopic laws are reversible, then for any entropy-increasing trajectory there is a reversed one. Zermelo invoked recurrence, noting that a finite system can, in principle, return arbitrarily close to its initial state. These objections were not trivial because they exposed the gap between what is possible and what is typical. The resolution is subtle and deeply physical because it depends on what is typical and what is prepared. Recurrence times for macroscopic systems are so vast that they dwarf cosmic timescales, and the special reverse states are never naturally selected. Even if recurrence is guaranteed in principle, it is irrelevant in practice, an answer that is mathematically correct and physically empty. Eddington gave the tendency a name that still carries weight. The thermodynamic arrow of time points in the direction of increasing entropy, and it is not a new force, just a direction picked out by overwhelming likelihood. Once named, the arrow becomes a lens, and you start seeing it in every ordinary asymmetry. Once you see that, everyday asymmetries look less mysterious and more structural. Cooling coffee does not choose to cool. It simply has far more microstates compatible with lukewarm equilibrium than with a hot, sharply defined gradient. The steam rising is not a preference. It is a diffusion of energy into the larger set of possibilities. The arrow also explains why memory works the way it does. A memory is a physical record, and making records increases entropy overall, because it requires energy flow and creates waste heat. A memory is not an ethereal imprint. It is a rearrangement of matter that must be stabilized against thermal agitation. A brain writing a memory changes synapses, a camera writes charge patterns, and a hard drive flips magnetic domains. In each case, the record is stabilized against noise by dissipating energy into the surroundings. The stabilization is the key. Without dissipation, the record would be as fragile as a pattern in smoke. The past is the direction where records already exist, and the future is the direction where they do not. We can read yesterday's traces because they have been physically written into matter and radiation. We are surrounded by evidence, some obvious, like a footprint, and some subtle, like a slightly warmer patch of air. This also explains why prediction differs from retrodiction in practice. The equations allow both, but the data do not, because the present contains many correlated traces of the past and almost none of the future. The asymmetry is not in the laws, but in the boundary conditions of what information is available. We have fossils embedded in rock, photons already en route from distant stars, and chemical signatures locked into ice cores. Even a room's temperature field contains faint information about what happened moments ago. If you could measure every molecule's momentum, you could read the room like a book, but real observers cannot. The future has no equivalent archive because it has not been physically written. Writing it would require entropy production, and that production happens as time advances, not in reverse. This is a quiet point with large consequences. The arrow is the direction in which the universe is busy making documents. The asymmetry is operational, not metaphysical, and that distinction matters. Physics does not need a cosmic now to explain why we feel time's flow. It needs only the way records are made and preserved. The feeling of flow tracks the growth of records, because records are what let before and after become meaningful. Now we connect this to the documentary's central question. What would it mean to stop time, according to physics, beyond relativity and Zeno freezing, where motion is slowed or change is interrupted? Thermodynamics suggests a new meaning, because time's direction is tied to usable change. If the arrow is what lets us define before and after through records, then stopping time might mean disabling record-making itself. That sounds abstract, yet it is intensely physical. because record-making is an engineered process of stabilization. A world that cannot stabilize differences cannot store facts, and without facts there is no operational timeline. A functioning clock is not just an oscillator, it is an engine that maintains a stable cycle against noise, and that stability requires energy flow to correct drift and suppress fluctuations. A clock must continually shed entropy into its surroundings, because otherwise random perturbations smear its phase until tick and tock lose distinction. Even an atomic clock, so precise it can sense altitude changes, must continually interrogate atoms, process signals, and dissipate heat. Lasers must be stabilized, electronics must filter noise, and the entire apparatus must be shielded from temperature swings. Accuracy is bought with resources, and the bill is paid in entropy. Clocks, like organisms and computers, live on gradients. A gradient is a difference that can do work: hot and cold, high and low pressure, chemical potential, or electrical voltage. Gradients are not just scenery. They are the fuel of reliable cycles, the reason a system can repeat a state instead of drifting. Work is what lets systems build and preserve order locally, even while the total entropy rises. Without gradients, there is no sustained process that can mark time, because nothing can reliably cycle. A pendulum without energy input becomes a quiet weight, and an oscillator without power becomes thermal noise. So the arrow is not simply about motion, and it is not simply about change in a vague sense. It is about the availability of free energy to drive irreversible processes that create records. If free energy is the currency, then record making is one of the most expensive purchases. Free energy is the portion of energy that can be converted into useful work at a given temperature, and it depends on constraints and disequilibrium. When free energy vanishes, the arrow loses its grip. You can still write equations with time in them, but you cannot build a device that meaningfully tracks that parameter. This is where cosmology enters, because the arrow is not only a kitchen phenomenon. The universe began in an extraordinarily low entropy state, and that boundary condition is the seed that makes entropy increase possible everywhere. The arrow is not merely local bookkeeping, it is a cosmic inheritance. The early universe was hot and dense, which sounds like high entropy, because hot gases feel disordered. Yet it was also remarkably smooth, and smoothness matters profoundly once gravity dominates the bookkeeping. The early cosmos lacked the clumps that gravity wants to create, and that absence is a form of specialness. Matter and radiation were close to thermal equilibrium, but gravity had not yet clumped structure. The cosmic microwave background still carries this message, an almost uniform glow with only tiny temperature ripples. Those ripples are the faint blueprint of everything that later became dramatic: stars, galaxies, and the long chain of gradients they enable. Gravity changes the meaning of disorder. A uniform gas is high entropy for short-range forces, but for gravity a uniform mass distribution is special, because there are many more ways to be clumpy. In gravitational systems, structure can be the path to higher entropy, not lower, because clumping opens vast new regions of phase space. Clumping opens up more gravitational microstates, because matter can arrange itself into countless configurations of stars, galaxies, and black holes. In gravitational systems, the deepest entropy reservoirs are not diffuse gases but collapsed objects with horizons. The arrow in this view is written into the universe's willingness to fall inward while radiating outward. As the universe expanded, tiny fluctuations grew. Gas fell into potential wells, stars ignited, and galaxies formed, and each step increased total entropy even when local pockets became more ordered. The order is real, but it is paid for by heat and radiation that spread into a far larger volume. Visually, the transformation is dramatic. An almost featureless fog becomes a cosmic web, with filaments of galaxies and dark voids between them. The arrow is written into that growing contrast. It is also written into the light itself, because every photon streaming away is a tiny carrier of entropy into the cold. Local order is paid for by larger disorder elsewhere. Stars shine because nuclear reactions convert low-entropy nuclear fuel into higher entropy radiation, and that radiation streams outward in vast numbers of photons. A star is a gradient machine, turning concentrated mass energy into a flood of lower energy quanta that fill space. Planets host chemistry because starlight creates a temperature gradient between sunlit surfaces and cold space. The day side warms, the night side cools, winds rise, oceans circulate, and weather becomes a heat engine. Even the simple act of evaporation and condensation is an arrow-shaped loop, driven by sunlight and ended by infrared emission. Life, metabolism, and computation are not exceptions to the second law. They are engines that accelerate entropy production while maintaining local structure, and that is why they can persist. The paradox dissolves when you remember the accounting is global, and life is a sophisticated way of spending gradients. A cell builds proteins and membranes, but it does so by burning chemical gradients and dumping heat and waste. A civilization builds cities and servers, but it does so by consuming concentrated energy and exporting entropy into the environment. The glow of a city at night is a visible signature of irreversible throughput, organized activity paid for by dissipation. In that sense, the arrow is not just an abstract curve on a graph. It is the reason flames burn, rivers flow, and living systems must eat. Because maintenance requires a one-way throughput. The arrow is also why repair is hard, because repair demands energy and produces heat, even when it restores local order. This cosmological framing raises the stakes. The arrow of time is not merely a human habit of perception. It is a global consequence of an initial condition, written into the universe's starting point. When we ask why time feels one way, we are also asking why the cosmos began with so much unused potential. We can now ask the hard question that hides behind every why. Why was the early universe low entropy, especially in its gravitational degrees of freedom, when so many other configurations were possible? The question is sharp because it is not about dynamics, but about the selection of a boundary condition. Physics does not yet have a final answer, but the boundary condition is empirically implied by everything that followed. The existence of stars, gradients, and long-lived complexity points back to a beginning that was strangely special. The smoothness was not merely aesthetic, it was thermodynamic capital, waiting to be spent. If the universe had begun near maximum entropy, it would already be in equilibrium. There would be no stars, no chemistry, and no observers to ask questions, because nothing would provide sustained free energy. The sky would be a nearly uniform bath, and the idea of history would be empty. The arrow exists because the beginning was special, and that fact is both powerful and unsettling. It suggests that time's direction is, at least partly, a story written at the boundary of the cosmos. We live inside that story, and every engine we build is a small echo of the universe's original imbalance. Now we push toward the bleak horizon, because thermodynamics has an endgame. If entropy tends to increase, what happens when it cannot increase much more, when the universe runs out of gradients to spend? The answer is heat death, a quiet end rather than an explosion. It is not a single catastrophe, but a slow flattening of differences until the cosmos becomes thermodynamically tired. Heat death means maximum entropy consistent with the universe's constraints. It means thermal equilibrium across accessible degrees of freedom, and it means gradients fade until no process can extract net work. In visuals, imagine the last bright structures dimming, galaxies thinning, star formation sputtering, and the sky losing its contrast. The universe does not shatter, it simply stops offering leverage. The colours of nebulae fade, the sharp silhouettes soften, and the night becomes less a tapestry and more a uniform veil. No gradients means no engines. No engines means no metabolism, no weather, no star formation, and no sustained complexity, because complexity is built from persistent flows. Even the idea of maintenance becomes meaningless, because there is nothing left to spend to preserve a pattern. It also means no reliable computation, because computation requires free energy and produces waste heat. Even if logic could be made reversible in principle, real devices face noise, and noise demands correction. The more you push toward lower dissipation, the more you become vulnerable to random thermal kicks. A computer is a thermodynamic device, not just a mathematical abstraction. Even reversible logic needs error correction in a noisy world, and error correction costs energy, because it requires discarding uncertainty into a heat bath. In a universe with no cold sink, the bath is everywhere, and every correction becomes prohibitively expensive. As equilibrium approaches, the cost cannot be paid, because there is no colder reservoir to dump heat into. The environment becomes as warm, in the relevant sense, as the device itself. When everything is at the same temperature, cooling stops being a process and becomes a contradiction. A clock is also a thermodynamic device. It must resist decoherence, drift, and random kicks by consuming resources, and those resources are always gradients that can be depleted. A clock is a promise to repeat, and repetition is never free in a noisy universe. A pendulum clock needs frictional losses replenished, a quartz oscillator needs power to sustain oscillation, and an atomic clock needs lasers, electronics, and stable reference cavities. Without energy throughput, the cycle loses meaning. The hands may still move briefly, but the motion no longer tracks anything stable, and the clock becomes a sculpture. This is the chapter's sharp clarification of time stops. Physics does not forbid parameter time in equations because the coordinate or proper time variable can still be written down. But without change that can be harnessed, time loses operational meaning for observers. If nothing can function as a clock and no records can be formed, then the arrow dissolves in practice. Time becomes a label with no physical handle, like a coordinate on a map of a land nobody can enter. The equations still speak, but there is no internal process left to translate them into experience. In that sense, stopping time is not freezing the universe at an instant. It is erasing the conditions that make before and after distinguishable to any internal observer. It is the collapse of time as a usable concept, because usability depends on memory, prediction, and the ability to compare states. Without gradients, comparison itself becomes impossible to implement. You cannot store a reference, you cannot protect a signal from noise, and you cannot amplify a difference into a durable mark. What remains is a universe where later is not forbidden, but it is no longer something any process can meaningfully point to. Now we bring back black holes, because they are entropy giants. A black hole's entropy scales with horizon area, and for astrophysical masses it dwarfs the entropy of ordinary matter by absurd factors. In a sense, black holes are the universe's most efficient entropy containers, simple on the outside, enormous in their bookkeeping. The idea that a black hole has entropy was once shocking, because black holes seemed like perfect erasers. Bekenstein argued that if you drop entropy into a black hole, the second law would fail unless the hole itself carries entropy. That argument was a turning point, because it forced thermodynamics to take horizons seriously. Hawking's calculations then revealed that black holes also have a temperature, and that temperature is tied to surface gravity at the horizon. With temperature and entropy together, black holes become thermodynamic objects, not just geometric traps. The horizon is not merely a boundary in space, it behaves like a system with state variables. When matter falls in, entropy bookkeeping changes, but the arrow does not disappear. The horizon area typically grows, and the generalized second law, ordinary entropy plus black hole entropy, still increases. The universe continues to choose the direction where the total accounting expands, even when the details are hidden behind an event horizon. Black holes act like sinks for structure and information in the thermodynamic sense. They swallow low entropy matter and contribute enormous horizon entropy, and that is not a violation of the second law. It is its extreme expression. A star's organized layers, its chemistry, and its gradients can end as a single, dark object with a vast entropy budget. Yet black holes are not eternal. Hawking radiation provides a slow leak, a quantum mechanism that makes black holes evaporate over immense timescales, far longer than the current age of the universe. The evaporation is faint, but it is relentless, and it converts concentrated mass energy into diffuse quanta. Evaporation converts concentrated mass energy into diffuse radiation, pushing the universe toward equilibrium. A once dark object becomes, over eons, a faint thermal glow that bleeds into the cosmic background. The arrow is visible in the direction of that conversion, from the compact to the spread out, from the storable to the ungraspable. We keep the focus on the arrow rather than the full technical detour. The key point is that black holes accelerate the universe's march toward a featureless state, because they store entropy and then return it as thermal radiation. They are not an exception to heat death. They are a major route toward it. As expansion continues and stars burn out, black holes may dominate the entropy budget. Then they evaporate, leaving an ever colder bath of photons and particles, and the universe approaches a thin, uniform haze. The last great gradients are spent, and the remaining differences become too small to power durable processes. In that far future, the arrow of time becomes faint. Entropy still increases, but the rate of meaningful change collapses, because there are fewer gradients left to power events. You can still imagine microscopic fluctuations, but they do not build into lasting structure because there is no thermodynamic headroom. Events become rare, and the capacity to build records vanishes. Even if particles still move and fields still fluctuate, almost nothing can be stabilized into a durable fact that distinguishes one moment from another. The universe has not stopped existing, yet it has stopped remembering. This is the quiet end promised by thermodynamics. Not a final moment, but a long fading of differences, a universe where almost nothing happens, because almost nothing can happen. The drama is not in a bang, but in an asymptote, a slow approach to sameness. Now we return to the laboratory, because the documentary's hook demands a lever. If the arrow is statistical and emergent, can we manipulate it locally, even if we cannot repeal it globally? Quantum thermodynamics suggests we can, within strict accounting, because small systems are noisy enough for rare trajectories to matter. At small scales, fluctuations are not negligible, and the boundary between energy, entropy, and information becomes experimentally tangible. A single electron in a circuit, or a trapped particle in a laser beam, can show entropy changes that would be invisible in a mole of gas. The arrow becomes a probabilistic slope rather than an iron rail, and that subtlety can be engineered. First, we state the constraint that keeps the story honest. The second law is not easily broken globally, and any local entropy reduction must be paid for by entropy increase elsewhere. Often the payment is hidden in an information register or a heat bath, where the waste is exported. The subsystem looks like it is running backward, but the combined system, subsystem plus controller plus environment, still marches forward. This is the modern thermodynamic lesson. You must draw the boundary carefully because the arrow can be disguised by moving the bookkeeping off screen. Maxwell's demon is the classic provocation. A demon sorts fast and slow molecules, apparently reducing entropy without work, as if intelligence could cheat physics. The story endures because it turns a philosophical itch into a concrete mechanism: measurement, sorting, and a door. The resolution is not that the demon is impossible, but that information is physical. To measure and sort, the demon must acquire information, store it in memory, and maintain that memory against thermal noise. A memory that is not protected is not a memory, and protection is an energetic act. To reset its memory and repeat the cycle, it must dissipate heat. Landauer's principle ties the erasure of one bit to a minimum energy cost, proportional to temperature, and that cost restores the second law. The demon can shuffle entropy around, but it cannot make the total accounting shrink. Modern experiments turn this story into protocols. Measurement plus feedback can extract work from fluctuations in small systems, such as colloidal particles in optical traps or electronic circuits near the quantum limit. The lab versions are not magical creatures, but carefully programmed controllers that use information as a resource. The entropy of the controlled subsystem can decrease temporarily, while the controller and environment pay the bill. The effect is real and measurable, but it is never free. When the accounting is complete, the arrow reappears, because the total entropy production remains non-negative in the relevant sense. This is not a loophole, it is a refined ledger. Entropy is not only about particles and heat, it is also about correlations, information, and what an observer knows and can exploit. When you know more about a system, you can extract more work from it, but acquiring and stabilizing that knowledge has a cost. In quantum settings, measurement backaction becomes part of thermodynamic flow. A measurement can create or destroy coherence, and coherence can act like a resource, because it encodes phase relations that classical mixtures lack. The arrow becomes sensitive to what is monitored and how feedback is applied, because monitoring selects which features become real records. When you choose a measurement basis and a feedback rule, you are effectively choosing which correlations you preserve and which you discard. That choice can bias trajectories, making certain transitions more likely in one direction and less likely in the other. The arrow, in this engineered sense, is not erased but sculpted. Quantum fluctuation theorems extend classical results into regimes where energy and information fluctuate strongly. They quantify the probability of transient entropy decreases in small systems, and they show that the second law is about averages and likelihoods. In other words, entropy can briefly go down, but the odds are exponentially suppressed as systems grow. The familiar arrow is the large number limit, where rare reversals become so unlikely that they never appear. In a microscopic device, a brief wrong-way step can occur, and you can even harvest it with feedback. In a macroscopic room, the same kind of step would require a conspiracy among trillions upon trillions of degrees of freedom. Now we connect this to the previous chapter's Zeno theme. Measurement can freeze change, but it also produces records, and records are thermodynamic. The act of watching is an entropy transaction. A detector must amplify a microscopic event into a macroscopic signal, and amplification requires energy. That energy becomes heat, and the heat is the physical footprint of a fact being created. The click of a detector, the flash of a photodiode, or the voltage step in a circuit is not just information, it is dissipation. We often imagine observation as passive, yet in practice it is an engineered cascade that leaves a thermal wake. In engineered systems, we can use that transaction to shape an effective arrow. We can design paths, drives, and measurements that bias trajectories, making certain transitions more likely in one direction and less likely in the other. The system appears to have a preferred direction, not because the laws changed, but because the environment was designed to reward one path. Superconducting qubits provide a concrete platform for this control. They are macroscopic circuits that behave quantum mechanically, and they can be driven and measured with exquisite timing, sometimes on nanosecond scales. In the visuals, the hardware looks almost architectural: golden traces, resonant cavities, and refrigerator stages descending into darkness. Their Hamiltonians can be engineered, and their coupling to environments can be tuned. With careful design, dissipation is not merely a nuisance. It becomes a tool that stabilizes desired states. Engineered dissipation can shepherd a system toward attractors, making certain quantum states robust against the very noise that would normally erase them. With engineered dissipation, a system can be steered into steady states that look like low entropy, relative to chosen variables. With feedback, it can be stabilized against fluctuations, as if the arrow were being locally narrowed. The narrowing is real, but it is purchased by exporting entropy into the measurement chain and the surrounding bath. The arrow becomes a controllable tendency within a designed boundary, and that boundary is the crucial phrase. The laboratory can create special conditions, but it must export entropy to maintain them. The more sharply you want to sculpt the arrow, the more carefully you must manage what leaks out and what must be dumped as heat. Researchers also explore shortcuts to a diabaticity and optimal control protocols that reduce dissipation for a given transformation. Less dissipation means less entropy production, which means a weaker arrow for that process. The arrow can be shrunk, even if it cannot be abolished, and the shrinking shows up as improved efficiency and reduced heating. The cost is complexity and control, because precision itself demands resources and careful isolation from noise, better shielding, better calibration, better feedback. Each layer is a thermodynamic investment. The irony is that to make a process look more reversible, you often need a larger apparatus that dissipates elsewhere. There are even special cases where effective dynamics appear time-reversed. Spin echoes and Loschmidt echoes can refocus defacing and partially reverse apparent irreversibility, revealing that some lost order was only hidden. In a vivid lab image, a pulse sequence is like a conductor's gesture, coaxing scattered phases to realign into a brief bright reappearance. These are not violations of the second law, because they rely on controlled pulses and carefully prepared initial states. They demonstrate that irreversibility is contingent on what information is accessible and what correlations are preserved. When you can keep the relevant correlations inside your boundary, you can sometimes rewind what looked like decay. In small, well-isolated systems, you can sometimes run a process and then undo it. The undoing requires precise control and low noise, and it fails as complexity grows, because uncontrolled degrees of freedom multiply. Each extra coupling is another place for phase information to leak, and each leak is another step toward typicality. The lesson is that irreversibility is not fundamental in the same way as energy conservation. It is emergent, and it becomes overwhelming when systems are large, open, and only partially observed. The arrow is a macroscopic regularity, and its reliability is a consequence of scale. This is the chapter's conceptual payoff. The arrow of time is not a sacred edict written into the microscopic equations. It is an emergent direction produced by statistics, coarse graining, and boundary conditions. That means the arrow can be manipulated, at least locally and temporarily, when you can control the boundary and the information flow. It can be blurred by reducing dissipation, and it can be redirected in effective descriptions by feedback and engineered environments. Yet the cost always appears somewhere. because the universe keeps its accounts. Information must be stored, erased, or exported, and heat must be dumped into a bath, because dumping heat is entropy production. So stopping time by thermodynamics is not about halting parameter time. It is about removing the gradients that let observers build clocks and memories, and it is about approaching equilibrium where the arrow loses operational meaning. The stop is not a freeze frame. It is the fading of the machinery that makes frames distinguishable. This returns us to the documentary's opening hook in a darker register. What if time is a switch physics can flip? Not by magic, but by turning off the supply lines that make direction tangible. Thermodynamics says the switch is not a button, it is a supply line, and the supply is free energy. When free energy flows, the arrow is sharp and life is possible because records can be made and maintained. When free energy dries up, the arrow fades and complexity collapses. The universe does not slam the door, it slowly stops offering leverage until change becomes too thin to use. We end with a transition that raises the next level of mystery. If time's arrow emerges from entropy and boundary conditions, then perhaps time itself is emergent, and the next chapter confronts quantum gravity and the problem of time head-on. What if time is not a river at all? What if it is a switch physics can flip, slow, or turn off? Our central question returns at maximum pressure, because every modern theory leans on time while quietly redefining what time even is. According to modern physics, what would it actually mean to stop time? And where could nature allow time to slow toward a standstill? On screen, imagine a river dissolving into a circuit diagram. The current still flows, but now it flows through gates, delays, and thresholds, components that decide when something counts as next. A second image overlays it, an atomic clock, its microwave transitions counting with ruthless regularity, while a black hole's horizon looms like a dark curtain. The clock's signal is clean, almost sterile, and the horizon is silent, swallowing light that tries to report back. We are not asking for poetry, we are asking for operational meaning, because physics only trusts what can be measured. Relativity gave us time as geometry, measured along world lines as proper time. Proper time is not a universal ticker. It is the time a physical clock accumulates along its path through space-time, and that path depends on gravity and motion. Quantum mechanics gave us time as an external parameter that drives evolution. In one theory, the clock is part of the universe. In the other, the clock sits outside the system, untouched by what it describes. That contrast sounds abstract until you picture the lab, where definitions become procedures. In quantum mechanics, we prepare a system, set t equals 0, and predict amplitudes at later times. We treat time like a coordinate on the wall, useful, stable, and not itself uncertain. In general relativity, the wall is not stable. The wall bends, stretches, and responds to the mass of the apparatus, and that bending alters what later even means. This is the conflict we cannot avoid at the frontier. Quantum theory assumes a background time to define states changing with t, and it uses that parameter to build interference, oscillations, and decay rates. General relativity denies any fixed background, because space-time itself is dynamical. Matter and energy shape the metric, and the metric shapes what any clock can mean. The metric is not just a stage light. It is a field with its own degrees of freedom, carrying gravitational waves and encoding curvature. When energy density increases, the geometry responds, and the response changes the separation between events. In plain language, gravity changes the spacing of time itself, and no coordinate grid is guaranteed to be globally meaningful. Even the simplest coordinate choice can hide physics, because coordinates can stretch while proper time stays honest. The contradiction becomes sharp when we try to quantize gravity. In quantum gravity, the clock must be a quantum object too, subject to uncertainty and entanglement. Yet if the clock is inside the system, we cannot use it as an external reference. Evolution becomes a question with no obvious parameter to evolve with, because the parameter is now a fluctuating degree of freedom. This is the problem of time. It is not a word game about philosophy, even though it sounds like one at first hearing. It is a technical obstacle to writing a unified theory where geometry and matter are both quantum. If you cannot define change, you cannot define prediction. And without prediction, a theory is only a diagram. In ordinary quantum mechanics, We write Schrödinger's equation and watch the state change with time. The Hamiltonian generates translations in time, and time is a given coordinate. We can treat the system as living in time, even if time is not an operator. That choice is not arbitrary. It is built into the mathematical structure of standard quantum theory. The Hamiltonian is the engine of evolution, encoding energy and interactions. When we say a state evolves unitarily, we mean probability is conserved as it flows through Hilbert space. The formalism assumes we can label slices of evolution by a parameter t, and that the parameter is not itself fluctuating. Even when we quantize fields, the background time coordinate remains the bookkeeper, quietly ordering creation and annihilation events. In general relativity, time is not a universal coordinate. Different observers slice spacetime differently, and no slicing is preferred by the laws. Diffeomorphism invariance means the physics does not care which coordinates we use. Coordinates are not physical rods and clocks. They are labels we paint onto a manifold, and the theory is built to ignore the paint. A clock in relativity is not a background label. It is a physical process, a world line, and a reading that depends on the metric. The metric is not fixed. It responds to stress energy, and that response changes the meaning of duration. Even the concept of simultaneity becomes local, because distant now is not uniquely defined. Two observers can both be correct and still disagree about which events are at the same time. So what happens when we demand both frameworks at once? We try to describe the universe with a quantum state, not just a subsystem in a lab. We also demand that the geometry defining time is part of that state. The moment we do this, the usual separation between system and clock collapses. The reference frame becomes a participant, and the participant cannot stand outside itself. At this point, the visual should tighten. The camera moves from a tabletop experiment to a cosmic panorama, then back inside the equations. We see a wave function spreading, then we see space-time itself rippling like fabric under a moving weight. The narrator's question becomes almost physical. If the fabric is quantum, what does it mean to say it changes in time? The result is a headline that still shocks even experts on first contact. In 1967, the Wheeler-DeWitt equation appears in canonical quantum gravity. It is associated with John Wheeler and Bryce DeWitt, building on the Hamiltonian formulation of general relativity, developed earlier by Arnowit, Deezer, and Misner. This was an era when physicists were learning to treat gravity like a constrained dynamical system, where not every variable represents an independent physical motion. The rough structure is simple and unsettling. Instead of I times a time derivative equaling a Hamiltonian acting on the state, we get a constraint. The Hamiltonian constraint acting on the wave function of the universe equals 0. The equation does not say, here is how the state changes. It says physical states must satisfy this condition. Time seems to drop out. The universe is described by a stationary equation, not an evolution equation. The formalism looks like a frozen universe, where the fundamental description does not mention now moving to later. When first encountered, it feels like a betrayal of everything dynamics was supposed to mean. It also forces a careful distinction between coordinate time, which is a label, and physical time, which must be read from something that happens. We must be careful with the claim. The Wheeler-DeWitt equation is not a final theory of everything. It is a framework-level result that emerges from quantizing general relativity in a canonical way. It also comes with technical baggage, factor ordering ambiguities, regularization issues, and deep questions about what the wave function is actually defined on. Even defining an inner product, the thing that turns amplitudes into probabilities, becomes a subtle piece of the puzzle. Yet the implication is hard to ignore. If the deepest equation has no external time, then time may not be fundamental. The flow we feel might be emergent, like temperature emerging from microscopic motion. Temperature is real, but it is not a property of a single molecule. It is a collective description that becomes meaningful only when many degrees of freedom are coarse-grained. This is where the documentary's hook becomes dangerous. If time is a switch, quantum gravity hints the switch might be off at the foundation. The universe might be timeless in its most basic description. That does not mean clocks stop ticking in practice. It means the ticking may be a derived phenomenon, not a primitive ingredient. A timeless equation does not mean nothing happens. It means happening must be redefined internally. Change must be described as correlations between parts of the universe, not as motion against an external clock. The universe would not be a film strip advancing frame by frame. it would be a complete object whose internal patterns encode what we call history. In this view, we do not ask what the state is at time t. We ask what one subsystem reads when another subsystem has a given configuration. Time becomes relational, built from internal comparisons. The language shifts from at 12:01 to when the pendulum points here, or when the cosmic field has this value. This is one route out of the freeze. We choose a degree of freedom to act as a clock, then describe other degrees of freedom relative to it. The price is that the clock is imperfect, quantum, and entangled with what it times. A quantum clock has spread in its readings, and that spread becomes part of the physics rather than an experimental nuisance. If the clock is noisy, then later becomes a probability distribution, not a sharp slice. The deeper tension remains. If the fundamental law is a constraint, where does the sense of evolution come from? Why do we experience a present that seems to move? The question is not merely psychological. It is about how a timeless formalism can reproduce the empirical success of time-dependent predictions. After all, our best experiments, from particle decays to atomic transitions, are built on rates, lifetimes, and oscillation frequencies. One implication points toward the block universe. In relativity, space-time can already be treated as a four-dimensional structure. Past, present, and future can be seen as equally real within the geometry. The present is not a universal slice. It is a perspective-dependent cut through the block. Quantum gravity pushes that idea further. If the fundamental description is timeless, then the block is not just a coordinate perspective. It may be the literal form of reality at the deepest level. The universe would be less like a story unfolding and more like a complete map, where routes exist all at once, even if travelers experience them sequentially. In a block universe reading, the entire history is a single object. Flow is not a feature of the world itself. Flow is a feature of how subsystems inside the block process records and correlations. A brain, a computer, or a measuring device does not access the whole map. It accesses local information, and it builds a narrative of before and after. This connects back to Chapter 5's arrow. We feel time because entropy increases and records accumulate. The present feels special because our memories and data are asymmetric, not because the equations privilege a cosmic now. The arrow is written into the distribution of correlations into which traces exist and which do not. A photograph, a fossil layer, and a detector log are all physical states, and they all cost entropy to create and preserve. Visually, we can show this with a simple motif. A trail of footprints appears in sand behind a walker, while the sand ahead remains smooth. The walker's experience is forward motion, but the physical asymmetry is the existence of records behind them. The footprints are entropy made visible, information about the past encoded in the environment. The wind begins to soften the edges, reminding us that records decay unless energy is spent to protect them. The block universe is not a comforting conclusion. It threatens the intuition that the future is open and the past is fixed. It also raises a technical question. If everything's a static structure, why do we ever need dynamics? Why do we write equations of motion at all rather than just constraints? Quantum theory seems to demand dynamics because we predict probabilities of outcomes as time passes. Yet in a timeless framework, probability must be assigned to correlations within the whole. The next moment becomes a conditional statement, not a moving frontier. Instead of what happens next, we ask what is likely, given this internal clock reading. This is a different grammar of prediction, and it can feel like learning physics in a new tense. This is the climax tension. We have slowed clocks with motion and gravity. We have frozen change with measurement and paid an entropy cost. Now quantum gravity suggests the deepest level might not contain time at all. The idea is not that time is merely slow, the idea is that time may be absent as a fundamental coordinate. We now shift from the Wheeler DeWitt shock to a different approach. Loop quantum gravity tries to quantize geometry without assuming a background spacetime. It keeps diffeomorphism and variance central, and it refuses a preferred external time. Historically, it grew from Ashtekar's reformulation of general relativity, which recast gravity and variables closer to gauge theories. That reformulation made the constraints resemble those of electromagnetism and the strong force, hinting that geometry could be treated with similar quantum tools. Loop quantum gravity replaces smooth geometry with quantum states of geometry. The basic objects are spin networks, graphs labelled by quantum numbers, areas and volumes become quantized with discrete spectra. The labels are related to representations of SU2, and the geometry emerges from how these representations connect. What looks like continuous space becomes, at the deepest level, an inventory of relational measurements that can only take certain values. On screen, the smooth grid of a coordinate chart fades. In its place, a web of lines and nodes appears, like a constellation drawn in 3 dimensions. Each link carries a spin label, and each node acts like a junction where quanta of geometry meet. The image is not a lattice in space. It is the quantum state that defines what space can mean. As the camera drifts closer, the web does not become a finer mesh. It becomes a different kind of object, more like a rulebook than a material scaffold. At the Planck scale, spacetime is not a continuum in this picture. Geometry is granular, like matter is granular in atomic theory. The continuum emerges only as an approximation when many quanta of geometry combine. The Planck length is unimaginably small, and the discreteness is not something you could see by zooming in with a better microscope. Any probe energetic enough to resolve that scale would itself curve spacetime violently, blurring the very notion of a clean measurement. This is not a claim that space is made of little cubes. The discreteness is relational and gauge invariant, tied to operators for area and volume. The grain is a statement about measurable geometry, not a naive lattice. It is closer to how angular momentum comes in discrete units, even though rotation looks smooth at human scales. The quantum numbers are not tiny bricks. They are allowed outcomes of geometric measurements. Time remains subtle in loop quantum gravity. The theory is built from constraints, reflecting diffeomorphism invariance. Without a preferred time coordinate, evolution is again not straightforward. The mathematics is telling us something. If you insist on a universal clock, you're importing structure the theory refuses to provide. The absence is not a gap to be patched quickly. It is a demand that we rethink what later is supposed to mean. The same question returns in a new language. If the universe is a network of quantum geometry, what does it mean for that network to evolve? What counts as change when the parameter time is not fundamental? Is evolution a real process, or is it a way of comparing different parts of a single quantum state? When we say the network updates, are we describing physics, or just our preferred way of organizing information? Loop approaches often use relational time as well. One field or degree of freedom is chosen as a clock variable. Other observables are then described as evolving with respect to that internal clock. In cosmological models, for example, a scalar field can play the role of a clock because it changes monotonically in many regimes. The monotonicity matters because a good clock must not run backward or pause unpredictably. This is powerful, but it is not free. Different choices of clock can produce different effective descriptions. The notion of time becomes context-dependent, tied to which subsystem we treat as reference. That dependence is not a bug. It is the operational meaning of time made explicit. It also invites a quiet humility. Perhaps the time we use is always a tool, never a God's eye coordinate. The payoff is a consistent respect for general relativity's core lesson. There is no external stage. The stage is part of the play, and the play cannot use the stage as an outside stopwatch. When we ask for a universal time, we are asking for a view from nowhere. Physics keeps refusing to grant it. Every attempt to step outside the universe returns us to the same rule. The observer is a physical system, and physical systems must be described within the theory. Now we connect to the promised bridge from chapters 4 and 5. If measurement can freeze change, why is the macroscopic world not Zeno frozen? Thermodynamics answered part of it. Uncontrolled monitoring produces decoherence and entropy, not stable freezing of all motion. The environment does not measure in the clean, selective way required for ideal Zeno suppression. In the lab, Zeno-like effects require carefully timed interventions and a controlled coupling to a measurement apparatus. In the wild, interactions are messy. They entangle systems with countless degrees of freedom, dispersing phase information into the environment. What looks like watching becomes thermalization, and thermalization drives systems toward typical macroscopic behavior. The same collisions that could, in principle, inhibit a transition also scramble the phase relationships needed to keep the system in a delicate quantum state. Quantum gravity adds a deeper twist. The environment watching is itself inside the universe. There is no external observer to define a universal time of measurements. What we call time may be a bookkeeping device for subsystems exchanging information. The very act of defining a measurement sequence assumes a clock, and the clock is part of the quantum story. If the clock becomes entangled with what it times, then the boundary between timekeeping and dynamics begins to blur. This sets up a radical idea that tries to unify the arrow with the absence of fundamental time. The thermal time hypothesis, associated with Ravelli and Kohn, proposes that time flow emerges from thermodynamics itself. It does not begin by assuming a clock. It begins by assuming a statistical state, the kind we use whenever we describe macroscopic systems. That starting point is familiar, because almost everything we know in practice is described statistically, not microscopically. The core claim is precise. Given a statistical state, there is a natural notion of time evolution generated by that state. Time is not a background parameter. Time is an emergent flow defined by the system's thermodynamic condition. In technical terms, the state defines a modular flow, and that flow can serve as the effective time for observables. The mathematics is sophisticated, but the intuition is plain. The state itself tells you what flow means. In this view, the clock is not chosen arbitrarily. The state defines a preferred flow through modular dynamics. The direction and rate are linked to coarse graining and to what information is ignored. In plain language, the way we compress details into macroscopic descriptions helps generate the very parameter we call time. The cost of a usable description is a loss of microscopic detail, and that loss carries a direction. This connects directly to entropy and the arrow. Coarse graining creates macrostates, and macrostates define typical evolution. Our ignorance is not merely psychological. It is built into the practical limits of any subsystem inside the universe. An observer cannot track every microscopic correlation, so the observer's effective description has a built-in directionality. Even a perfect computer would need energy, memory, and error correction, physical resources that themselves obey thermodynamics. Visually, the documentary can make this feel concrete. A high-resolution image of swirling gas is gradually blurred, turning into smooth gradients of pressure and temperature. As the blur increases, a clean arrow appears, pointing from sharp structure to uniformity. The arrow is not drawn by hand, it is drawn by lost detail. The camera can linger on the moment where patterns vanish, because that vanishing is the birth of a macroscopic time direction. Thermal time reframes the documentary's central question. Stopping time might mean driving a system toward equilibrium where no thermal flow is defined. If no gradients exist, the emergent time parameter loses operational meaning. A perfectly equilibrated state has no preferred direction of change, because it has no macroscopic contrast to define before and after. The system can still fluctuate microscopically, yet nothing macroscopic distinguishes one moment from the next. It also reframes the Zeno cost. Measurement produces records, records produce entropy, and entropy defines the arrow. The flow we feel may be the same phenomenon as the growth of thermodynamic information, not an independent background. If so, then trying to halt change is not just fighting dynamics, it is fighting the conditions that make time meaningful. The question becomes unsettling. If you erased every record, would time still feel like time? Yet thermal time is not universally accepted. It is a proposal about how to recover time from timeless fundamental laws. It is compelling because it ties time to what observers can actually access. It also invites a hard question. If different observers have different coarse grainings, do they inherit different effective times? And if they do, what does it mean for two observers to agree that an event lasted a certain duration? Now we turn to the beginning of the universe, where time itself seems to break. Classical general relativity predicts a Big Bang singularity, where curvature diverges and the theory stops. In that regime, the equations are not merely difficult, they are undefined, because the quantities they require become infinite. The singularity is not a place we can visit in the mathematics. It is a signpost that says, this description has reached its limit. The singularity is often described as a point in time, but that phrasing can mislead. It is a boundary of the classical description, a place where geodesics cannot be extended. It is the sign that the theory is being pushed beyond its domain. Quantum gravity is expected to change that story, because quantum effects should matter when densities approach the Planck scale. When energy is concentrated enough, the vacuum itself becomes active, and geometry can no longer be treated as a smooth classical field. One radical approach is the